with the scholars. So I invite Dr. D. Bhagwan to kindly start with the session.
So, very good morning all. Since 4 days we are discussing about biomass, its extraction, carbon sequestration, pyrolysis, byproducts, oil, chemicals, aqueous medium and different pollutants whichever come out from them and their applications, right. So, today we are going to focus on chemicals which we can extract or which we can prepare. This is not extraction. So, this is not a direct extraction. Here we are going to prepare the chemicals from the biomass whichever readily available in the environment and which we are considering as like during my earlier session also I have covered pectin, one of the material which is going to extract and having different applications. Similar way here also we are going to see one more compound such as lignin basically. So, we already discussed about cellulose and hemicellulose and their applications. And if we see paper industry, so most of the cellulose whichever extract from the wood, they will use for paper making, and the remaining lignin part what we are doing currently. What is the application of lignin as of today or how we are managing it? So, if we see that we are just sending it for combustion and there is no other applications, we are using it for energy generation purpose. But apart from that, we can modify that lignin compound into a value added material such as solvent, edible product like chemical product, and why we so these are the different value added materials can be generated from that waste lignin. So, this is the topic today, and now can we think why we need to generate these chemicals from this lignin? Is it necessary to our country? Because whenever we go for any funding or any research, we need to think what might be the applicability and what is the benefit to our nation, because whichever research we are doing, everything is from the public fund, right. So, whichever government fund we are receiving, that is public money. So, whenever we do our research in the similar way, we need to pay back to them, right. So, now why we need to concentrate on this lignin? So, first thing is one like environmental concern, means whichever waste generating from this paper industry, if we throw them or if we burn them like under uncontrolled condition, if we go for open burning, obviously it will create environmental pollution. Apart from environmental aspect, what might be the another thing? Why we need to convert this lignin into chemical compound? What is the need of that study? Very good. It has the potential to act as a resource. Then other than that, so if we don't go for lignin, then what is the current trend? For suppose if I say X solvent or X chemical which are extracting or converting from the lignin, then what is the status today? What we are where we are getting these chemical compounds as on today in the market? So, how you are or where we are getting all those chemical components? If we see the chemical industry strategy, all the solvents which were required for the processing of pharmaceutical bulk drug industries, so and food grade industries, they are importing from the different nations. So, most of as in case of pectin also we are doing the same thing. Similar way, whichever chemicals are we have the resource of potential to generate them, but still we are importing them from the other nations. So if we continue this strategy, then we will move towards. So it is not a sustainable development if we depend on other nations. Every nation should have their own resources and own production. So if we depend on them, then like we already face the COVID-19 issue. So during that phase also we had so much of issue with the methanol as well as different chemical components. We are not able to import them. For that, like for those chemicals, we are depending on China. So due to international ban, we are not able to import them. So under such conditions, our production will get damaged. The production cycle will get disturbed. That will not have like show the good impact on the nation's economy. To overcome all these problems, whichever materials we are today like facing as a waste that has the potential, so that can be converted into such chemical components. So sir has already covered all those topics like different different materials and different technologies how we can convert into. But if we see this, here you can see the agriculture crop residue which we are generating, and we already know the pollution status in Delhi. So and the burning of all these agriculture waste creating problem, and it is having particulate matter as well as greenhouse gas emissions. So and if we and whenever we go for production in the same ratio, we will be generating waste as well. So if we see the waste generation, annual crop residue which is we are having surplus, like some sort of agriculture residue is going for cattle feeding and some other applications, even building application, briquette manufacturing, and even yesterday we also gone through the pellet making and carbonization. So this is very minute quantity we are processing, because this agriculture waste is like wider spread. So collection and processing, like we are not having sophisticated facilities to process them. So we are not going towards this pelletization and carbonization. So the simple technique is go for open burning. With that we are managing, but that is not a sustainable way. So here we have this much of waste where has the potential to generate these many pollutants. And if you see the ratio as per IPCC, 1 ton of crop residue has the potential to generate 1.5 tons of CO2, means like more than the 1:1 ratio. So here if we go for open burning, it has a potential like as sir said earlier, he has given some examples where the carbon of the atmosphere is going to get captured by algae, right? So that the same material, means the chlorophyll content, when it dries and when it goes for open burning, again it is emitting the CO2. So this is not like the carbon neutrality or carbon negativity is going to get damaged, means destructed. So here we can manage this lignin and we can, so first thing, the environmental problem of all these particulate matter, SOx, NOx and other gases are going to get rid of. So these all chemicals sir has, like all these valorization techniques sir has discussed. So today we are going to see only the catalytic valorization of lignin compound. So what does it mean by catalytic valorization? Can anyone? What does it mean by catalytic valorization? Cellulose, hemicellulose, this part already covered, so I am not going to focus on that. So here we'll see only this lignin part. So this is the small monomer of the lignin portion. If we see the lignin molecule, so lignin composition in hardwood, it will be varying from 18% to 25%. This percentage of lignin is also going to vary depending on the quality of the wood. And softwood, it will contain 28 to 33%. and herbaceous plants it will have 17 to 24%. So here feed, and if we consider agriculture waste, where our agriculture waste will fall, most probably it will fall in the softwood. Like these are soft materials which are going to cultivate in the farmlands. So they will fall in this range. Means we have almost 1:3% of material which can be, and the thing is lignin is recalcitrant components which is not possible to degrade by biological process. So that is the disadvantage. But here by catalytic process we can degrade them and we can convert into value added components. So this is the complete polymeric structure of the lignin, where it contains 5O4 linkage. So every compound can be considered as a monomer. So this is the polymeric chain of lignin, and it contains 5 type of linkages. And if we break down these linkages, so can you think what can be the product? So if you cut down these linkages, then we will have the beautiful monomers, means the chemical aromatic components as well as carboxylic components, which can be utilized as a chemical product or edible product, and which will be used as a solvent in the industry. So those chemicals also we will look into. And so this is our motto. So now we know about the problem, and this is the structure, and our motto is to cut down these pieces. So how it will be possible to cut down the polymeric chain of this lignin compound? So here we are having different catalytic process where the chemical reaction is going to cut down the particular polymer at different junctions. So carbon-carbon junction or carbon-oxygen junction. So this is the carbon-carbon junction, this is the carbon-oxygen junction. So and each junction has, so here we are giving 5 different junctions which are representing with the this lignin polymer, and they have the bond dissociation energy. So every component has their own energy, like even in physical state. So if I want to cut down this bottle, then it requires different energy, and if I want to cut down this plant, it requires different energy, right? So and different even material as well. So with sharp one, like the small piece of any knife I can cut down this, but here we need some machinery to cut. So the similar way here also the breakage of bond requires, they are having different bond energies to dissociate. So these are the different bond energies which are required to make them this polymeric compound into monomeric components. And one of the beautiful thing is this lignin compound, the most abundant compound is beta O4 linkage, and the bond dissociation energy is also very less. So it is only 55 to 65 kilocalories per mole. So that is the energy which requires to break down the linkage. And if we, and will it be possible to break down only this linkage beta O4? Because this is not in the pure form. Whenever we extract lignin from the agriculture waste, first we'll go for separation of cellulose by acid digestion, followed by alkali digestion. We will separate the lignin, and whichever remain portion retains with the solid phase, that again goes for acidification, and further it will become as a lignin pure compound. And this lignin is a polymer. It is not having only beta O4 linkages, it also contains alpha O4, beta linkage, beta 5, 5 linkages. This 5 represents the carbon 5 of the different aromatic rings. So under such conditions, like with increasing carbon content, the breakage is becoming more hectic, and breakage of 5 linkage is very hard to break. And this is in case of different components, catalytic components we are discussing about. And now, so if we break down these polymeric lignin compound, and if we degrade or if we break down linkages at all these 5 groups, then we will have, these are the product materials, and this can be considered as a synthetic product of the lignin. So synthetically, like whenever we start experiments, first we can do experiments with these chemical components, and followed by we can go with the real lignin compound. So if we continue this, then we will have the idea where our particular catalyst is working and which product we are getting. We will have the basic idea and clarity about the mechanism, So after that we can start working with the real lignin. If we directly start converting real lignin, then it will be more complicated because it is not having a single linkage or single bond. It contains multiple bonds and multiple linkages. So the understanding will get differed. So first we can work with these compounds, and further you can go with the realistic lignin component. So these are the different conversions are already discussed. And this is particularly for the catalysis of lignin transformation, which like different ways how we can convert this lignin into different components. So if we convert them using ionic liquids, then we will have benzoquinonic components. And if we go for pyrolysis, so phenol compounds, and if we go with gasification, syngas and hydrogen we will be getting. And if we go for oxidation of these lignin, then we have a chance to get valine and valinic acid. So valine means the edible product which we generally use as vanilla. So this valine which we importing today, we have the potential to produce this, but still we are depending on other countries and we are importing. And next one is acid catalysis, and methoxyphenol, catechol, phenol components. So just we are breaking this polymer into smaller components, monomers. By that way we are getting all these compounds which we are importing or we are depending on other nations. That dependency will reduce, and our production rate will increase by converting all these things. And base catalysis, so syringol and catechol. And if we go for supercritical fluid, then phenolic components. And if we go for metal catalyst, then hydrocarbon and gaseous components are possible to generate from the lignin. So these are the different mechanisms and their byproducts which are possible to get from the lignin waste. And this is one of the reactor, like at 215 degrees temperature under controlled conditions, under anaxic conditions, they have converted into all these monomeric components. So this is the real field sample. So as I mentioned, whenever we go for real field sample, we will get more products. Means it will break down whichever catalyst or whichever reactant we are using, it will break down wherever it wants to be. And as I mentioned, energy, like BO4 linkage is like it requires very less energy, so every beta O4 will get cut down, and after followed by that, if we have bunch of electron, then it is going to break down the other linkages which are present with our lignin. So then how to rectify this problem? So today we are like carrying this experiment at the lab scale. So we will get some synthetic sample and we'll go with the synthetic sample. But we are thinking about nations, right? So when we think about nation, then and we are having environmental problem as well. So under such conditions, we need to think how we can deal with the real lignin component. So then under such pressure, which technology or which methodology will work. So if we need to go for real sample, then how to control this reaction? Because all chemical reactions we know, once we start the reaction, obviously it is moving forward, right? So like backward reactions will not be possible under this oxidation technology. So then how to control? Here we can control our mechanism to get the selected component. Here if you see, we are having list of components, but we need only vanillin because it is having high economical market and it is useful in pharmaceutical industry, it will be useful in food industry, right? And currently we are depending on others, so that dependency will reduce. Then how to get only vanillin apart from all these components? How we can, even you can see the percentage of the component. So vanillin only we are getting 30% out of the lignin degradation, lignin oxidation, and here 24%, 20%, all these different acids we are getting along with the, in a mixture form. So how we can control this like formation of all these monomeric components? If we control this, then can you imagine how the economy will grow, like how the economy of India will grow? Like it will have massive growth because we are basically agriculture based industry and we are having so much of agriculture waste. So if you develop such a technology which can convert this lignin waste into a value added product, then whichever raw material is readily available, and if we pay very minor charge to them, then the waste will reach to your processing plant. And you can process that waste, and further you will generate so much of economy, which will enhance the growth of country. So now, here with the help of photocatalytic technique, as I mentioned, this comes under catalysis technology. So here, in catalysis, we are also inducing the photon energy. So chemical catalysis can also do this processing of oxidation of the lignin, but here we are inducing the photon energy along with the catalyst. So by that way, we are having control on the oxidation of lignin. That is the first part. And second part, whichever compound, like recalcitrant compound, we are considering as recalcitrant, that is also going to cut down into monomeric component. So here, like we already know about the solar energy, how the solar energy works and how the solar panel works. The similar way, so here we need to use semiconducting materials to generate the electron energy, where the electrons, they are going to move from valency bond to conductive bond. When the photon energy hits on the valency bond, it will excite, and the electron will pass from valency bond to conductive bond. And this transformation depends on the band gap of that particular semiconducting component. So this is the, if you think this is one semiconducting component, for example, the basic semiconducting compound is TiO2, basically like widely used and widely accepted compound. And apart from that, we can also consider different components such as even ZNO also can be considered as a catalyst for photocatalytic reactions. So when it exposes to light, UV light, and this catalyst can work under UV light as well as visible light. So then how we can mimic these two reactions? For suppose today in laboratory scale, we can continue with the UV reactors or UV light intensification. But what about like in massive scale production, UV light may not be possible, and your cost is also going to be more. So to reduce that, even the same catalyst can be developed to or converted into visible based catalyst, where it has the capability to the only character we are going to change is the capacity of absorption of that light is going to increase. So if it absorbs UV light, then it will work under UV. So this can be decided based on simple experiment like UV visible spectrophotometer. Just by scanning, we can identify whether it is absorbing UV radiation, UV light or visible light. So with that we can decide, and further experiments can be carried. So here, whenever it exposes the generated electrons and hole at the valency bond, electron at the conductive bond, and now these two are available, and now is this electron if interacts with the oxygen of our solution. So for that purpose, so whichever solvent we are using, we need to aerate that, or if it exposes to the air, then oxygen, obviously it will be getting dissolved with the solvent. So whichever oxygen available within your solution, that will get converted into superoxide radical. So here superoxide radical is available, electron is available. If there is no oxygen, then where this electron going to move? It will retain with the conductive bond, and after some time it will dissociate or it will recombine with the valency bond. So like this is the continuous reaction. There is no restriction in between the transformation of electron. It may recombine or it may transfer to the aqueous phase where the oxygen is going to convert into superoxide. So this reaction, now we are having 4 elements, and here the reduction of photo oxidation of H2O is going to take, photo reduction of H2O2 is going to take place, and it will convert into hydroxyl radical. Now we are having 4 species which were generated from our semiconducting material. One is electron, it is reactive species. Second one is superoxide, this is also one of the reactive species. Here OH hydroxyl radical, and fourth one is hole. And all these reactive radicals, reactive oxidative species have the different energy levels. And now, as I discussed earlier, we are having, if we have the selective energy dissociation bond competitive radical, then we can convert polymeric compound into monomers. That is our aim. And if you see this reaction, we are having different energy levels with the different components, means different reactive oxidative components. So if we control this mechanism, then we can beautifully cut down our polymeric compound into monomers. So then how we can control this reaction? As I mentioned, the generation of electrons or the retaining of electrons with the conductive bond without recombination, it depends on the bond gap of the particular compound. So here, as chemical engineering or mechanical engineers, they first think about the band gap of this particular catalyst while they are designing. While they go for any synthetic process, first they think how the band gap is moving towards, if it is increasing or decreasing. So ideal one is for titanium oxide, it will go from 3.0 to 3.2 milli electron volts, and for zinc it will go to 3.2 to 3.3. So this is the ideal band gap generally available. But whenever we think about selective component, selective band gap, then we need to design our experiment in such a way that where you can reduce this band gap, or if required we can extend the band gap. So that will be for homogeneous catalyst. First, suppose at homogeneous stage, if it is not possible to maintain this band gap, then we need to have a catalyst with heterojunction. Means we can combine. First, suppose we are having, like, we thought to use zinc oxide, because zinc oxide will be like cheaper when you compared with titanium dioxide. So zinc oxide and band gap will be more, so 3.2 to 3.3 electron volts. So but our requirement is if we reduce it into 3.0 or 3.0102, so how it will be possible, how we can reduce this? So during synthesis process, we can dope this with the any other semiconducting material which will have less band gap competitively with zinc. And second option will be doping this zinc oxide with the conductive material. So by that way we can enhance the transformation of, because whenever band gap increases, the transformation of electrons will consume some sort of energy. So if you reduce this band gap, then you can save the energy of the electron energy which was generated. So that energy can be used to cut down the lignin compound. So while thinking about these designing of experiment, we need to see which chemical compound, which heterojunction can help us. So if we decided that, then we can move on. So as I said, we are having these reactive species, superoxide radical, even electron hole also have the capability to cut down the lignin compound, and one more species is OH radical. So if we continue with reactions, then we can prepare aromatic monomers like vanillin and all those components, alkalines and alcoholic components, methanol, ethanol, propanol, which we are importing. So all these solvents can be converted or can be generated from the waste lignin, and organic acids, formic acid, acetic acid. So here currently this one is the eye washing thing where we can have the carboxylic, like monomeric and dimeric acids, which can be utilized for different applications in the bulk drug industries. So for bulk drug applications, we basically depending on China. So here if we produce these chemical compound, then it has so much of potential to for marketing. So this is one of the area. And benzene derivative. So benzene derivative will be like, it's very tricky thing, because in benzene derivatives we need to cut down only the aromatic ring. But in case of organic acids, you can cut down into n number of pieces. So if we cut down into, like, the basic thing is here you can see we are having aromatic ring, but here you no need to think about aromatic ring. So it can, if you use such a material to cut down this lignin into n number of pieces, so that your organic compounds like the polymer compound will convert into organic acids. So that is one of the like beautiful thing where we can explore more. But the thing is, we need to think about the catalyst. Here only catalyst is going to play role. So if you select design a suitable catalyst for this, then it will work for. And second thing is whether your catalyst is stable or unstable. If it is stable catalyst, then you can recycle it for n number of times. If it is unstable, then it is going to like degrade within 2 or 3 cycles. So again, that is also one of the thing. And generation of same chemical, same catalyst with the same reaction condition is not possible. Like it will change. So because of that, titanium, like it's like the longest one and the older one, still we are depending on titanium, because the characteristics of titanium, every synthesis it is going to change. Means it will, whenever you change precursor, whenever we go for different controlled conditions, operational conditions, obviously the character of that catalyst is going to vary. So better to have like more amount of catalyst with the same batch, so that we can process the same catalyst for n number of samples. And this is one of the catalysts which were prepared from the zinc oxide. So where the same methodology, the conventional methodology, sol-gel methodology has been utilized. But the beauty of this catalyst is it has the porous nature where the lignin has been trapped and it has been degraded in controlled conditions. So as I mentioned earlier, it basically degrading with the controlled beta O4 linkages and converting into a single component with the highest rate of conversion. As I shown in the previous results, the percentage of vanillin is only 30%. But in this case, we are having more than that. So nearly 70 to 75% of that vanillin has been produced from the lignin compound. So just I want to show how the this new compound formation has been identified. So you can see here, this is UHPLC peak where we do for organic analysis. So if you see the retention time at 0.32 to 0.39, we are having small peak at initial stage. So once we add this compound catalyst into your solution, obviously it will start interacting with your lignin compound and it started reacting. And the next one, when we start the reaction under photocatalytic intensification at 3 hours, you can see the peak height. So this height gives you the concentration of that particular compound at that particular time. So you can compare with these two ones. So this is the initial one where the initial without photocatalytic reaction, the new compound formation has been identified, and the next one shows the increment of that particular compound at the same site. And with increasing time interval, you can see here, and the next one, the concentration has been increased. And the same thing continued up to 18 hours. So here you can see we are having 3 layers, and this is the extended 3 layers. So this is at 17, 16, at up to 18 hours, you can see the new compound formation at the same retention time. So which indicates the M by Z ratio of that particular chemical compound indicates the oxidation of that lignin is taking place, and we are having a selective compound. So this mechanism we generally call it as selective oxidation of that particular compound. So whichever catalyst we develop, it has a capability to cut down at the selective sites. Means the energy which it gives is specifically cutting down the lignin compound. And as I said, this as some chemical reactions may have forward reaction, backward reactions, but here it is only the one-way reaction. There is no backward reaction. So for that we are having proof that, so we continued reaction up to 18 hours, and after that I retained that sample for 4 days. This is an unintentionally done experiment. Like I think during holidays I kept those samples in lab, and after that again I have did the analysis, repeated the analysis, and found, you can see the comparison. So this compound formation catalyst is still working without photo intensity. This catalyst have the capability to continue the reaction. So here it says that if you don't use proton energy, then also your catalyst have a capability to continue the reaction and convert the component. So the same thing happened here. The concentration of new compound has still increased, and there is no backward reaction. So if backward reaction happens, then it is not like suitable for industrialization. So if you continue the reaction, if you leave the solution for separation or some other purpose, then also your compound formation is going to continue, and it will not again recombination or oxidation or reduction of compound is not going to take place. The original compound will be retaining within your solution. Here you can see this is the initial lignin component which we have used. So the retention time is nearly 4.5, and here you can see the final analysis of that same sample. So, and here there is no peak which were we identified at initial stage. So this is the initial peak, means the lignin compound which identified at 4.5 retention time, and the second one is the final analysis, means 18-hour, after 18-hour analysis, where the new compound, like the total compound has been shifted from retention time of 4.2 to 0.33, means, and M by Z ratio is also going to change. So this represents 150 M by Z ratio selectively, the selective components. And here you can, like with this pictorial view, we can say the compound conversion or compound formation is very selective and suitable. Means like if you target if you go for this reaction, then we can generate only the selective target compound from the polymeric chain of lignin. So with this, this is the this is the lab scale studies which we carried. But the same thing, if we continue with the semi-pilot, then it can be continued up to the pilot scale levels. And as I am mentioning, along with compound conversion, new compound formation concentration has also identified. So here, if you see this orange peak, we are having highest conversion with the concentration of 0.75 gram per liter. And compound formation, you can see this pink line. So with increasing this one, the compound concentration has also increased. And somehow here, it is having different trend. It might be some because of uninterrupted oxidation state, uninterruption, or maybe because of different other oxidizing radicals which are releasing into or which are participating into the reaction. But after that, the continuous conformation has been carried even up to 24 hours, it is going to get with the stable production. So the conversion of lignin into new product has been continued up to 24 hours. Still there is no deactivation of catalyst. Even without photo intensification also, it is working towards the conversion of depolymerization of lignin at selective site. The beauty of this research is it is going to cut down the compound at the selective sites. And now, as I said, we need to control the reaction. Means we are having 4 oxidation species which are generating in the reaction, and if we control them, then obviously our reaction is going to control and the selective species. So as have shown here we are having somehow decline in the conversion, but conversion is taking place, but new compound formation has been declining. Means some reactant involving or disturbing the conversion into new compound. So to identify this, I have also done the quenching reactions where we can control the different oxidative species, and by that way we can identify which species is responsible for this conversion. So here we identified superoxide radical is the responsible species where it is going to help for the conversion of this particular lignin into selective compound. So So if we see this graph in, so this is the new product formation. So conversion, like at all reactions, you are having respective conversion rate. But if you see the new product formation, only we are having new product formation with two reactions, means without any quenching reagent, we are having new product formation, means we might be having 4 different oxidative species, they are participating in the reaction, so it is going to have their conversion rate. And the second one is with hydroxyl scavenger. So with hydroxyl scavenger, scavenger means the hydroxyl component is going to convert into water with the help of isopropyl alcohol. So in the same reaction, during the reaction we will add some sort of alcoholic species, so which can react with the like hydroxyl species which were generated from the photocatalytic reaction, and because of that it will become, OH radical will become as H2O molecule. So if it converts into H2O, then it is no more available for the reaction. So here we are controlling that. So means when we control that, the remaining compounds, so here the remaining species is superoxide, which generated from the O2 to superoxide. So that superoxide is continuously generating. So because of that, new product formation has been identified with our reaction. And the next quenching agent is superoxide radical. So for superoxide, we have used benzoquinone, where benzoquinone is going to associate with the superoxide and it will convert into again oxygen. So when we use this superoxide scavenger, so there is no formation of new product. So with this reactions, we came to know the reactive species which is involving in the oxidation of this lignin at selective site is superoxide species. So this is the controlled species. If we specifically generate this, then we can design our experiment to get the selective product. So that's how it has been carried, and we have generated vanillic acid at to 65 to 70% yield. So again the purification, we can get the 99% pure compound, but the thing is, and still it will have, like it is having some sort of designing or developmental aspects, so where we can enhance the production, because here the conversion rate is 99%, but we are yielding only 60%, means 30% loss still we are having. So if we control that 30%, then we can yield the good amount of aniline with the pure compound. If we go for, like when we enhance the concentration of this particular selective compound, obviously your impurities will get reduced, right? So that is the one of the good thing, where we can convert the whole lignin, whichever we are considering as waste, can be converted into value added chemical compound. Here we are converting into chemical, like different solvents or different food grade components. And if we see that vanillin having pharmaceutical applications, where it is, and this will be used for flavoring purpose or additive component, and next household applications, and for different synthetic processes. So whichever chemical we are, or the vanillin which we produced from this lignin have different synthetic applications in the pharmaceutical industry, and food flavorants which will be used in the bakery applications. So these are the different applications which can be generated, which the material which can be generated from the waste, and the like currently we are considering it as waste as well as environmental problem, but it has the potential to convert them into different chemicals as well as solvents. So that is the thing, but only the backbone of this study or the conversion is we need to design the selective catalyst, then only it is going to have this selective breakage or selective oxidation of your lignin polymeric compound. By that way we can generate it into selective compounds. So this is how the waste biomass can be converted into different value added components. So is there any questions? I will be happy to. Is this fine? Yes, please. Obviously, it is possible when we go for designing of the catalyst. So, and the second thing is light which we are using. So, at selective wavelength, we have a capability to generate. It enhances the selective oxidation species. So, if we are using 365 nanometers with the selective range, with the filter like exact filtration rate, then we will generate the selective oxidation species under catalyst like designed catalyst. So by that way we can enhance our yield. So whichever we are saying like 60 to the gap 30%, we can reach up to 80% such that. But still we are having aqueous medium. So whenever we go for all these controlled conditions, still there is a problem with the oxidation species. So sometimes it may excite more. So by and intensity, if intensity changes, then obviously your electron bunch is also going to change. Like the energy will differ. So if the energy differs, then obviously the breakage is also going to be uncontrolled. So sometimes if you are having 70 kilocalorie per mole, so if you have that much of energy, then it will go to the next linkage. Because whenever we have high energy, then we go to the higher selective sites. But the lower one, obviously it is going to degrade. Like obviously it is going to get oxidized. It will cleave that linkage, but the same way it will cleave the another linkage. So that can be controlled. That can controlled by intensity of the light and wavelength of light and the catalyst. So these three are the major play rollers in our like photocatalysis process. So many catalysis methods already available. Catalysis is already available. The problem is in catalysis process, like it is not possible to control. So once we start the catalysis, then it will catalyze into, moreover it is going to create the acid components. Means selective aromatic compound, like it is very less to have in our sample at the end of the reaction. But in photocatalysis, we have an advantage, we can generate the selective species, selective radical species. So that is the advantage of this photocatalysis. Even catalysis process have like different, it can generate so many components, but like the selectiveness is going to change. Because if we target one compound out of this polymer, then it will give you good economical value and it will have the even purity as well. So whenever your yield increases, obviously the remaining compounds are going to get down. So by that way you can reduce the, first suppose here as I said superoxide radical helping us. First suppose superoxide radical is not participating in the reaction and only the reactive species is OH radical. Then how we can control? During early stage, like I have mentioned, if we expose our, if we use aqueous medium, if we allow air into our medium, then only oxygen species is going to exist with our system. So if you create anoxic system and if you use organic solvent, then oxygen, like without oxygen, then you can mimic the generation of the superoxide and you can reduce the generation of superoxide. You can have only hydroxyl radical in your system. So by that way also we can control. But in this reaction we are having, like we have proven, superoxide is acting as a selective catalyst, as a selective radical species. So by that way also we can control the conversion rate and we can enhance the yield. Thank you.
Thank you, sir, for such an insightful talk and for shedding light on lignin photocatalysis and the potential of lignin. We will begin with our next session shortly, so kindly be patient.
हेलो हेलो। आ तो रही, हिल रहे हैं। हेलो हेलो। इसको चढ़ता है किसी? ओ कुलदीप, नीचे से चढ़ता है किसी? हेलो हेलो। कम आ रही बहुत। आई तो पूछ रहा हूँ, नीचे से कोई छड़े जो। कौन बोल? हेलो हेलो। हाँ सर, पता नहीं, शायद आ तो रहे हैं। वंश ने बोला होता कि वैलिड, हाँ वैलिडेक्टरी के लिए सर ने, भगवान सर ने बोला कि आना ही पड़ेगा, आप नहीं आओगे तो फिर। उनसे पूछना है कि चेक किए कि नहीं। हेलो 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 हेलो। हाँ मैं बता दूंगा एक बार आपको। हेलो।
As we move forward, we welcome Professor Sandeep Kumar, whose engaging lectures have enriched this program. So without any further ado, I now invite Professor Sandeep Kumar to deliver his talk.
ऑफ है क्या? चलेगा, मैं इसे कर लूँगा, छोटा हटा दो, मैं इसे कर लूँगा. Okay, so good morning everyone. How was yesterday? Like it? Manipal. They have some unique facility, especially on pyrolysis, and 3 reactors at different size were there. Am I right? One was lab scale 100 gram level, another was kilogram level, another was little bigger, and then they are building one more. But what you saw that everything was on pyrolysis, okay, and they are taking lot of wood waste and all, and they are trying to build a bigger facility where they can demonstrate good amount of oil, which can be used as a sample for further application and testing another thing. If you do at the gram level, we don't get enough material to test in engine or fuel or anything, but we do more research. But it's a kind of transition, okay, lab to bench, bench to pilot, pilot to commercial. That's the step you go. And what you see that's a facility, okay. You can do so many other things. Like I was telling that it's good for torrefaction even. It's a reactor, fixed bed reactor, continuous reactor, auger reactor. So you have to take it like that. But the idea was a very good connection, because we had talked pyrolysis a day before, and then you could see in action and you could see the samples. Okay. So while it's a very vast topic, hundreds or more than years of work is there. My work is also more than 10 years, and everyone is working, so it's very difficult to cover in 3 or 4 days. Okay. The idea was to start the discussions. Today this is my last session. I'm here down little longer, but this one I'm just trying to see where we stand. Okay, and again we make interaction. So carbon capture and storage, we talked, and this is kind of a need of the hour. Many projects are going on, and you can see that carbon capture and storage is called CCS, but we moved from CCS to CCUS. So what is the difference between CCS and CCUS? So yeah, CC is carbon capture, U is utilization and storage if you need, or sequestration. So we have started with a storage, and there are many places you can just store. It may not be possibility of utilization, but wherever we have, we should do CCUS. And if you are doing CCS power plant as the biggest emitter point source, you have to find out. Okay, disperse non-point is difficult, but if you have a point source, then you can implement few things. Try. Power plants are the point source, okay, where you burn coal or natural gas and you have CO2. So that's where we should focus. So post-combustion, oxy-fuel and pre-combustion, there are three different approaches how you can reduce CO2 emission impact, all right. So it's kind of process engineering or more where to do that CO2 can be, emission is less. Oxy-fuel combustion is oxygen, otherwise it's management here. IEA, how many you know IEA? International Energy Agency, okay? And they look at fossil and both sides, okay? So their prediction is iron and steel by 2030 CCUS 4%, 2050 25, 2017 and cumulative 25%. So we are talking carbon emission and we are talking bioenergy, and I am showing iron and steel. What is the connection? Because iron and steel needs lot of heat in the process, blast furnace, kiln and other things. So that's a CO2 emission point. So can we reduce that? Okay, it's not just thermal power plants. There are many other places where we emit a lot of CO2. Cement, kiln process. So there also we are targeting. Chemical industries, there are many industries where carbon intensive. So we are looking at, we have started with fuel only, fossil fuel and road transportation, but we realize that industrial decarbonization are equally important. And this is part of industrial decarbonization. Fuel definitely, power generation is definitely. So global funding trends, you will see that blue hydrogen, ammonia, natural gas processing, BECCUS, what does it mean? Bioenergy, carbon capture, utilization and sequestration. One of the example you saw yesterday, bioenergy, pellets, carbon capture in char, utilization if you are making filter or somewhere or some chemical, or oil we are talking you can burn, or they were extracting some chemicals from the oil. So that's utilization, and S is storage or sequestration. So you saw BECCUS in action yesterday. When we teach in class, it looks like what's going on, all right? But this is simple to understand. A lot of focus is gone on bioenergy side. Some of the startup, there are many more startup, but some of those are here. Green light carbon technology, direct air capture, that's biological sequestration. CO2 utilization in concrete, cement I was talking, so cement industry is also heavy on CO2 emission. So bioenergy, biomass gasification technology have improved efficiency. Like BECCUS, where I was saying you can gasify, pass through Fischer-Tropsch, and you can make it fuel. When we are talking fuel in the future, we are talking drop-in fuel, not much blend fuel. Focus is shifted more on drop-in fuel. And biomass gasification gives you drop-in fuel opportunity, because you will produce syngas, pass through Fischer-Tropsch, and you will get diesel, which is as good as petroleum. Lot of focus on biomass plus other feedstock also. We realize that there are many more than just biomass, food waste, paper waste and other things. So non-traditional biomass sources like municipal waste are increasingly explored wherever we find. That's why we call this organic waste, IMWAJ. These are numbers, I will not go there. So in India, you will know better than me, but I try to list it what's going on. India is the fastest growing bioenergy market, and energy expanded to account for 45% of total energy consumption by 2030. Policies such as mandatory blending obligation for compressed biogas ethanol blending target 20% by 25 or 26. Now you can yourself answer point 2 where we are saying that 20% will be mandatory. Are we there? I don't see there, am I right? I don't know. If some states might be doing, but it's not mandatory. These are optional. So we set the target, is same in across the world. We try to meet it. If not, then we extend the line, because saying is easy, but there are we able to produce that much? If you don't have that much production, then how to do 20%? CCUS is growing here. Initiatives such as National Bioenergy Program, Satat M2 energy is going on. Emerging carbon decarbonization focus is also come, not just transportation. Industrial decarbonization means steel making, cement making, paper. These are the high, means point source of CO2, I can say that. So CCUS are being done. This one yesterday, day before yesterday, I was saying, don't have to be, there are startup ideas here, right? Not just research, fuel and all. There is a lot of opportunity. So Ministry of Power in 2021 put a guideline that thermal power plants should have 5% of renewable in that. Now you see steel, cement, all these industries, they need energy. And natural gas or coal was the source. They are mandated to do 5% of renewable or bio part or waste, organic waste part. So you will see that NTPC, they have most thermal power plant here, right? So they are running around where to get this bioenergy, 5%. Where to get, how to implement in their system. So 5% means 95% coal, 5% biomass. But you will have to develop an engineering system, all right? Boiler are designed for coal only. Now you are adding 5%. 5% may look less, but it's a huge amount if you look at the scale of power plants being operated. That much organic waste or biomass need to be arranged. Now what is best with blending for coal? We discussed before. If you want to do co-firing, this is an example of co-firing or direct firing, you can say that. So what is the best way to blend biomass with coal? If you take sawdust powder, which we saw yesterday, so many chips, so mix with coal, will it mix? Put in conveyor belt and fly it, it will separate, am I right? So you need pellets. Just for transportation easiness also, you need pellets. Now you have choice, raw pellet, biomass pellet or torrefied pellet, all right? Raw pellet, everyone knows they can make it. Torrefied pellet, Manipal University can make tomorrow, but not many places, right? You need to have a facility. Torrefaction. Torrefaction is low temperature pyrolysis. So now the startup or business part of it, many companies want to go in this direction. Can they make pellets, torrefied pellets, torrefaction plant? I know 1 or 2 companies, they set up quickly and they develop, I think, 10 ton per day plant already. And power plants need assurance. Let's say tomorrow they started 95 and 5% ratio and after 6 months they cannot find 5%. Then it's not going, am I right? It's disruption. So those kind of things, business opportunities are there, but if you can get a contract and you can be sure on inventory, that's the opportunity. So torrefaction, why torrefaction? Because it gives you 1.3 times the energy densification. When you transport, you are transporting more energy. When you are blending with carbon, coal, you are blending more energy into that, and still it is cleaner. So this is easy business and lot of demand. With 5% you will do calculation, lot of amount of biomass is needed. This is how torrefied biomass will look like. Gasification, if you remember I was talking about syngas can be fermented. carbon monoxide and hydrogen can be fermented to make ethanol. Looks little weird. Normally fermentation means liquid, right? But syngas can also be fermented. And if you go through gasification route, you break down all organic biomass in syngas. There is no lignin or this and that, right? So it's 100% carbon gone into syngas or CO2, and you cleaned it and then methanol. So efficiency looks better. If you go biochemical route, then you need to do pre-treatment, lignin will not take part in saccharification, those kind of things. So LanzaTech is the company. They mastered gas fermentation technology. They have their proprietary microbes, and that's where they built it. So I think they are leader on that. Waste to biofuel, sustainable aviation fuel from municipal solid waste. So what is sustainable aviation fuel? Have you heard about that? Aviation fuel, you know aviation fuel? Jet fuels, little different than diesel. It's a diesel range, but it's tuned for aviation. So suddenly, or not suddenly, last 5 years focus have shifted more on sustainable aviation fuel and marine fuel, shipping and that industry. The road transportation fuel is kind of getting secondary, more on aviation. The reason is you are getting lot of electric vehicles. So the growth might be shrinking, means may not need that much biofuel, ethanol, because if everyone goes in electric in next 10 years, your opportunity getting lower. But in aviation, I don't see we are going to electric anytime soon. So jet fuels are needed. And jet fuels, if you go through sustainable aviation fuel, we called it, then it's coming from biomass and renewable. So SAF, in short, it's called SAF. And lot of companies are working on, can we use organic feedstock to make SAF. Same thing for marine. Huge shipping, you see that container and big ships you will see in ocean. They are not powered by electric, and I don't see that much we power electric. So again, marine fuel and SAF are the opportunities where companies are working. Poets Biofuel, Poets is a company, it's a big ethanol company, monopoly kind of thing in the United States. So they are on corn to ethanol, but they are building plants where corn, stover and other grassy material can be used for ethanol. So these are the major companies working. So LanzaTech process, you get syngas from gasifiers. You will have a gasifier. You get syngas and then compress. This is a fermenter. That's their proprietary microbe. And what you get is ethanol. But now ethanol, we say that in future we want jet fuel more than ethanol. So there are processes coming up, ethanol and convert to jet fuel using catalytic process. So there are many companies taking the second part of this, a startup. They are focusing on ethanol to jet fuel. ETJ they call it, ethanol to jet fuel. European companies, they have stake, Clariant, UPM Biofuel, also one of the year. So diesel, I was saying a lot of focus was on biodiesel, sometime back, biodiesel, still biodiesel. But again, if you want to rely on future, we want drop-in fuel, not blend, biodiesel, not biodiesel, 5–10% is fine. So how do you make drop-in diesel or renewable diesel? So if you remember, biomass is hydrogen deficient. So you take oil, and this oil, this is coming from paper sludge, but this oil can come from any grease, waste cooking oil, seeds which we don't eat, non-food vegetable oil. Do some cleaning. To the hydro treatment, means hydrogen plus catalyst. Upgrade it, comes to the fuel grade. Fractionate is like a distillation, and you will get diesel. This is also commercial process. UOP is the huge company, they make it in Europe. So have proprietary catalyst here, so that's why they make a lot. So anything green material, oil material, LG put it here and you can get jet fuel. Department of Energy and many other departments across, they are looking at aviation and marine sector. If you are looking at ground transportation, again I say here we are looking a lot of ethanol, blending 10%, 5%, but in next 5-10 years it's going to shift. Because answer is coming for ground transportation because of batteries. But there are no answers coming for jet fuel or marine fuel. So if you are looking at a future, researcher will look for future, this is the way to go. Either biologically and all, focus more on aviation fuel or marine fuel, which are good. And they all have benefits of reducing greenhouse. This is the target for United States, 60 billion gallon, they will get it. Indian companies, Praj. How many of you know Praj? Pune based, you will know. Yeah, you know. So they are ethanol company and kind of monopoly here in India. Everywhere you will see Praj technology they have. So they work on ethanol. It was sugar cane, now sugar bagasse and all the agriculture residue they are focusing on. So they might have their own enzyme and cocktails of fermentation and other thing, but they are the huge company to follow. Indian Oil have a dedicated biofuel division, but they are on thermochemical process. So prior more on biochemical, this one is thermochemical. Reliance is more on thermochemical, but they also do bio. Bharat Biogas in compressed biogas. So these are the company leading here. CCUS carbon capture, Tata Steel focusing on steel production process, how to reduce. I know some other sector also they focus on how to reduce carbon emission. Indian Oil has CCUS, so CO2 to methanol. This is utilization. You capture CO2 and convert CO2 to methanol. CO2 to methanol have many different processes to do. One of the is electrochemical reduction. You can do that, okay? And that's again a not commercial process, but it's quite advancement. Pilot scale it has been shown. So future researcher, we are focusing on food feedstock. If you are working on food base, that's not the future. That's not the. So it's called fourth generation. We have started first, second, third, fourth generation, but nowadays first generation or advanced. If you say advanced, it covers third, fourth. Is not to get confused. So always keep advanced generation and pyrolysis, gasification, or digestion route. Anything you can capture CO2, capture, sequester, or make fuel. Go to hydrogen, methane, synthetic biofuels. We talked what are the different processes, but that's kind of a black box. We start from here, advanced feedstock, and you get drop-in fuel. Again, I am emphasizing. A drop-in fuel in this case will be SAF, sustainable aviation fuel, renewable diesel, those kind of things. Ethanol is good to go, but then you have to move ethanol to ETJ process, ethanol to jet fuel. You will see many companies coming on ethanol, so I'm not saying, but as a researcher, we are looking down the line 10 years or 20 years. That's the future. So challenges is cost, especially existing plant like Tata Steel, they are trying to do, Reliance, Adani Group, and many other groups. It's a IOCL and other thing. They have existing facility. Now they have to set up something to do that. So cost comes. How big a scaling comes, so that depends on how much government support financing comes, how much they can take on. The CCUS project cancellation rates exceed 78% due to cost, and that is true. Many CCUS project in United States started very big and they ran out of ideas or money, so that's struggling. And just you are adding cost to existing process. Biomass prices may rise 20% by 2020 due to competition for non-traditional feedstock. So everyone is running around municipal solid waste now. Even if it is free, you have a get money for hauling, but it's not going to be true. If we are moving to a jet fuel and all, we need have a whole lot of MSW. So the cost will come. The more we grow, it won't be free. Collaboration opportunities are there. There are many industrial clusters. There are many big projects in Europe where they have a consortium. US also has consortium. So there's a lot of opportunity there. So if you want to look at the United States sites, what they are doing in Department of Energy, you should be looking at, just Google this program. Okay? All technology what I am talking, they are listed there. The processes, more detail, what projects, whole lot of details are there, what they funded over the time. It takes time to dig in there. Their program area is renewable carbon, which we are talking. It's a general theme. Then they go more detail on conversion, CO2 utilization, bioproducts is another focus. Definitely bringing AI, ML, data simulation, other thing, integration, system development. System development means I develop a process for fermentation. The other one is how the logistic will come. So how entire system will look like. That's a big thing. Transportation fuel. Transportation fuel is moved to SAF and marine fuel. So here is the link, even if you have it or not, you remember this biotechnology office, DOE, Google it. I was talking, we are looking for postdoc position, future and all. Any funded project gets listed here, announced there. So that's where you can see, okay, this group, this company, this professor got funded, so that's what you can look at that. So maybe good idea to have RSS feed of this. Just subscribe weekly, monthly, and you will get it. Go to this website and then RSS feed. New companies, what updates, even if you are funded, any path-breaking results came out, it's announced, major publication. So this is a good resource kind of a one place to see lot of things. India also have their own site, MNRE, Niti Aayog site and many other places, but this is bigger, much bigger than that. Just much I have today. And I am leave it for discussions, and I really enjoyed this and many more than this. Okay. So questions, we have another 15-20 minutes. I see lot of enthusiastic researcher here, early, mid-career, faculty and everything, very much focused on environmental. So I really enjoyed your hospitality, interaction, and the idea is continue networking. Let's keep building our link and do that. And if you need anything, just email me. I'll try to answer as much possible. Yeah. Yeah. So ethanol to jet fuel, you go through dehydration process. So it's a thermal process and catalyst, and that catalyst comes as a proprietary or innovation, part of innovation. If you are looking for research direction, then look at for what catalyst promotes dehydration and polymerization to long chain. So ethanol is 2 carbon, right? And jet fuel is 14, 15, 16, 12 carbon. So you are building chain, dehydration, joining. So it's more on catalytic research and plus combined by distillation. So the researcher will focus on catalyst development in that area. And then the focus, if you want to go, lot of industry is moving towards electrochemical reaction processes. So that's another promising down the line 15-20 years where we want to move thermal processes to electricity. The reason is renewable electricity is getting cheaper, availability, energy storage is getting better. So why to rely on burning or combustion? Why not electricity, which is cleaner? So the future state of art I said that, and the down the line roadmap you can say SAF, marine, electrochemical processes, electrocatalyst, these are the direction you want to choose, which will be, to me, it looks like another 5, 10 years, 20 years in that direction.
Because always we think of transport sector, use of biodiesels and all. We never think of jet fuels.
Yeah, but
Yeah.
biodiesel, how much will last? Can you imagine? If we started putting charging station in next 5, 10 years a lot, you will see lot of explosion of electric vehicle. You already see scooters and auto and all. So once you move to electric, who will take biodiesel? How much they will take? The another biodiesel did very well, but the reason is it's a blend fuel. You will not see cars running on 60-70% biofuel, 10 or 20%. So you limit yourself. But if you have a renewable diesel, so going, and aviation has no answer yet. If you look at the research, GE or all top companies, they are doing electric aeroplanes, lot of, but nowhere close to in our lifetime or maybe other part of that. Marine, same thing. It's a huge, huge ship. You will see that. And fuel requirement is a lot. And fuel requirement is little bit different because aviation has different requirement, and this is shipping, water side has a different fuel requirement. Okay, so these two fuels are picking up, and we should focus on that, how much we can contribute.
Sir, we said about two different processes, anaerobic digestion process, another one is aerobic digestion process. In anaerobic digestion process, it is without air, about 45% CO2 is generated. But aerobic process, it is with the atmospheric air. What is the percentage of CO2 there, sir?
In aerobic, we are losing carbon in form of CO2, am I right?
Yes, sir.
You are supplying, our idea is if you want to make fuel, you want to preserve carbon, that's where anaerobic comes, where you have methane. Okay. And there you will see 60-40 ratio, average I am saying it may be 56-62 also depending on what feedstock and condition. So that's for biogas. And aerobic is not done for biogas normally, okay. It's for more and other things. Again, I want to add on biogas also. We are moving to biogas vehicles, CNG and all, but transition is how to go to liquid fuel. The processes are there, lab scale. Even biogas, people have tried to change it to diesel. CH4 plus CO2, that's what you get if you clean it up. CH4 conversion CO2 catalytic, people are looking at that. At high temperature, CH4 plus CO2 is converted to syngas using dry reforming process, 600, 700. People are looking at how to bring it down. So imagine you are looking at biogas coming from digester, CO2 plus CH4, and if you have some catalyst at low temperature, photocatalytic or something, just if you can tune that CO2 to CO, you got an opportunity to change into liquid fuel, because CO2 does not burn, so you will get more carbon efficiency. So again, that's the direction. If you are focusing on digester, let's focus on how change CO2 to CO. That's another way to do that.
Just I was comparing the CO2 emissions from both processes. So for around 45% in anaerobic. What is the percentage, approximate percentage or raise for the?
Frankly, I have not looked at aerobic what they do, because
Yes,
I focus on biogas and
yes,
all.
sir. Right.
And aerobic will definitely be less methane, so emission will be less, because methane is more potent.
Because somewhere when we are writing the research papers, we are comparing the carbon dioxide emissions to the atmosphere. So that's why
definitely. So in aerobic, anaerobic means absence of oxygen.
Absence.
So you are preserving carbon in methane, which is more potent. If you emit, if you need fuel, then you need that. Aerobic means you are oxidizing carbon such that it does not go to CH4. So their emission will be less even if you leave it.
Thank you, sir.
If we are doing composting, we are preserving methane emission, am I right? If you don't do composting, then these things are going to degrade and contribute to it. So composting helps at the lower level, our community level. Biochar helps further. If you do biochar, you do much more than that. Any more question?
You did mention about ethanol, blended ethanol. So like whenever I come across with this blending mechanism, so we conducted one survey in Pune itself. So it was like question comes regarding purity of the ethanol. If it is not enough pure, it will produce more greenhouse gases. So how to deal with that problem?
Pure means you will get pure ethanol from fermentation, right? When you blend with petrol, so you are blending. So I don't think purity is a question.
But most of the people, they do talk about purity of the ethanol. So that is like that
That's
part
a
is
common language may be talking, but what I said that the ethanol has lower heating value. So energy value coming down, that might be talking.
yes.
So it has a reducing the efficiency, other thing they may be showing how much you have to yield.
Yes, yes.
Okay, that might be the reason. But
Yes.
purity in fermentation, typically biochemical process gives you much purer than thermochemical processes.
Yes, yes. Thank you.
You are adding only 5 or 10%, so it don't. No, it's simple math. One is 44, another is 30. So you do 95 into this and 5 into this. It will reduce, but it may not reduce a lot. When you start adding more, then it will compromise more. Yeah, so at 5%, it will be little less impact than the other percent.
Now, government allows around 10%.
Yeah, 10% in United States also is a 10. Here it allows, there it is mandatory. So the difference is, if you make mandatory, you will be filling up, all right? If he allows, then I have a choice, take it or not it. Then it comes the question, someone thinks it's not pure, so I'll not take it and other things. But if you make mandatory, you will take it. Yeah, the heating value is simply how much you blend, just two equations you can put it, percentage.
Good morning, sir. Sir, what is the future of advanced biofuel like second generation and third generation biofuel in India?
In India is doing a lot on biofuel, right?
Yes.
That's what we are talking. Ethanol is coming up. Praj industry is working a lot on grass and bagasse to make it. Maharashtra Belt Sugar cane bagasse is going focused on ethanol. So good future is there. I'm saying that. What I'm saying, even down the line, if you can produce ethanol, ethanol can be made to jet fuel also. Government supports is a lot. I see a lot of programs coming up, National Bioenergy Program and other things. So investments are going on. It's a good future. Yeah, Praj. And I showed you that bioenergy, NTPC, Ministry of Power mandated 5%. You think 5% is a small amount? It's not. If you take 1,000 ton per day coal and 5% of that, that much biomass you have to add, you will struggle to secure within 50 kilometer. You may not have that much. So it's a big change, big boost for torrefaction and bioenergy if NTPC and other start putting the 5%, and they are planning to make it to 7%. So a lot of business opportunity came, all right. Rural sector where all these feedstocks are left over or have low value bedding and other application. Now you supply to NTPC or any other power plant, you get pricing local. The good part of bioenergy or biofuel is local job creation. Ethanol, again, ethanol is good for blending 5-10% and that, but if you want to go make a bigger impact, we need to go 100%, all right? Biofuel, I'm not talking ethanol. If you want 100% biofuel, then you want some fuel which is directly go to pump and pump it, no blending. Okay, that's why I was saying advanced biofuel or SAF, sustainable aviation fuel or marine fuel are important. So ethanol is doing good and it will keep doing good, but we want to transition further, not 5 or 10 or 20%. complete change. So that
So you continuously mentioned that these are business opportunities, entrepreneurship opportunities here. So, but what would be the investment and what is the kind of the labor that would be required?
I need to yeah, that's
Like, what would be the monetary investment in on these projects? Be it
if I
making.
were, I look at a Startup India schemes, what they have. I'll write a proposal, look at the build a team who looks technology, who looks business, who can look at all these things. Build a team, put a company, look for government, and under this guidelines, Ministry of Power, you connect with them. My startup is going to support these things. You'll have a better chance. So a startup is technology plus business. How much you can make it? It's not just technical. Am I right?
So, but you were talking about these projects could be implemented in rural areas as well. But if we required a skilled labor, I'm not saying
Yeah, I
that
get
the
it,
labor
yeah.
there is not skilled. We can teach them. But initially, how do we take up the project?
So I'll really tell everyone, look at Husk Power a story. How they, this is one of the early success story. That's why I'm saying it's nothing to do we know or not. Look at their success story, how they built. These two guys were from, happened to be Bihar, but they were in US. One is electrical engineering, another I don't remember. They came back just seeing this opportunity, and they built an empire in that sector, and now they are great supplier to African country. So they came with business idea. It didn't matter. They didn't know biomass. They are electrical engineers, but they see that this is the gap, and we can do that. And so business or a startup requires open mindset, not just lock down the research questions only. You have to move on. So what I am saying here is 5% torrefaction, and someone can reduce as a cost and supply at a lower cost to NTPC or whatever company, then they have a business there, right? You come with some other feedstock which no one has seen yet, and you have a kind of a guaranteed security that you will get that. One of the big challenge is biomass securing feedstock. This year you can get, next year it may change, price may change, and then you have a agreement for let's say $100 per ton. Next year it is 120, they will say, because weather difference. So these are the challenges. It looks simple, but even building a plant you need feedstock. Then transportation come, logistic comes, farmers come, policies come, regulations come. So it's a different, but entrepreneurship interest. If you have little bit, these are the opportunities. And wherever training and other thing comes, you can definitely train them. There are many universities where you can bring an skill set. So that's not the running a plant. We run thousands of plants, right? Different chemical sectors and all. We just all these processes are either running fermenter or those pyrolyzer or gasifier, all right, and some catalyst. If you are given training a week in Manipal, you will run that pyrolysis process. It's not big deal, so you can train that. Nowadays, it's more automation. So you have a centralized control system where you will watch and let them work. AI has yeah, Napier grass, bioenergy. How many of you remember Jetropa? Might be you remember, am I right? It came big for biodiesel, and Indian Railway started doing that, diesel engines and all. The problem came, can we grow so much to get Jetropa? And it turned out to be the seeds were fine, but it was cakes and all were toxic. So you could not give it to feed animal feed. So then what you to do? So you are looking at the doing processes. So the process of conversion was not a challenge in Jetropa. The challenge were growing, this toxicity, handling, and other things. So barrier. This is the entire life cycle you have to look. I remember many we are growing a big Jetropa farms in African country. They secured land and they made it. It came big, but it faded away. LG also have opportunity if you are working in there, because LG will give you proteins, oil, and that oil can directly go to jet fuel. You don't have to do pyrolysis oil and then upgrade and all. You can directly do conversion to that. There are companies which are working on how can modify biologically which can give directly long chain hydrocarbons. Arizona is a big Department of Energy bed there. LG to they call it HCATI, AGTAI or something like that. So big farmer there. So LG brings lot of opportunity. Macro LG also coming up, lot of opportunity in that.
What is your comparison opinion about us and your department student, that how we see biomass as a fuel?
So we are going out of GIAN. So comparison about
Us and your student in your department,
so
how we both see biomass as a fuel.
biomass as a fuel.
What is our approach comparison to that?
I think same. There are a lot of things here going on, and I see much more energy here than by a student who can. Yeah, yeah. There's a lot of approach is fine. Yeah, and many of our students are from here only. They gave either from here or other universities. So, yeah, and I'll tell you, PhD or down the line thing is, if you like it, then only you will do PhD. You like the field. So any student either here or there, they like that topic, environmental. That's why they will do. Otherwise, there is enough job outside, they will do. Why you put 4 or 5 years of PhD, which you may not like it. All right. Just degree does not give you anything. If you are PhD, then you know the topic, then only you will get a good job or anything.
Any other questions?
If not, then thank you everyone. I'm still around next few hours, so it's okay to interact. Okay. Easy quizzes. Just to do some icebreaker. Okay, so let's see how well you do. Okay. And these are very easy. What is the family purpose of carbon capture and utilization? Making products and renewable products, utilization means you are making ethanol or some products. What technology is used to capture CO2 directly from atmosphere? DAC, all right? Direct air capture. What is a common product made from captured CO2? Anyone? If we have CO2, what common products we can make? One I just discussed. The company name was IOCL or something. CO2 to methanol. And if you remember Fischer-Tropsch, you can keep building longer chain and alcohol, so you can make ethanol also. So these two can be made.
Both.
Methanol, even methane also. So A and B. How does CCU support renewable energy integration? How does CCU support renewable energy integration? You utilizations you capture and you can integrate with energy storage, batteries and all right? So by utilizing excess renewable energy to power capture processes. So any capture process you can integrate with electricity also. What is the role of hydrogen in synthetic fuel production? Yeah. Which of the following is a benefit of using synthetic fuel? They are cheaper than conventional fuel, they reduce greenhouse gas emissions, they increase energy efficiency, they are less efficient than conventional fuel. Synthetic fuel, they reduce greenhouse, that's why we go renewable, am I right? And we talked this one a few minutes back. What is the main difference between CCS and CCU or CCUS? S is just store, U is utilize also, all right? So basically by utilization, you bring some economics in a right way. Just a store means you spend money, but here you have some byproducts also. What is the key application of captured carbon in construction? Concrete making. So CO2 you can capture in concrete. So low carbon, what is that? Carbonated building materials. And it captures for a long time, concrete, am I right? You build a building, then CO2 stays long time. True or false? Carbon capture and utilization involves storing CO2 underground. If it is S, then it is okay, but it is U, so you are not storing. Synthetic fuels are made from captured CO2 and renewable hydrogen. Yes, CCU does not support economic growth. False, am I right? Carbonated building materials is again repeated one, are more durable than traditional materials. It is says that, but not proven, so I will say false at this stage. CCU is a substitute for carbon capture and storage. It's wrong, it's U. The same thing, carbon capture utilization involves converting CO2 into, give me one product name. Okay. Primary purpose of CCU is to reduce greenhouse gas emission. Carbon capture supports renewable energy integration by utilizing excess renewable energy to power maybe power plants or something like that. Yeah, so there's something missing here. Captured CO2 can be used to produce renewable fuels like methanol or ethanol. The main difference between CCS, CCU is that CCS focuses on storage while CCU utilizes, and if you make CCUS, then utilization and sequestration or storage. Captured carbon is used in the production of low carbon concrete materials or something like that. Okay. So these are simple questions, might be confusing by words, but you should be able to answer now. Thank you.
Thank you, sir, for your thought-enriching lectures and for this wonderful quiz. These 5 days have truly honed our skills and knowledge. We are taking back with us a bag full of learning, perspectives, and inspiration to apply in our journey ahead. We will now take a short tea break. Please join us outside for some refreshments. And please be back in 10 minutes. It's a very big bag.
So the bag we can.
have Head, Department of Environmental Science, Professor Lakshmi Kant Sharma. With over 18 years of research and 15 years of teaching experience, Dr. Sharma is an expert in the application of optical, microwave, hyperspectral, and LiDAR data for environmental monitoring and sustainable development. His research contributions span a wide range of areas, including climate change studies, forest fire modeling, wetland ecosystem assessment, biodiversity conservation, and disaster management using advanced geospatial technologies. He has published over 100 peer-reviewed articles and book chapters, including in the top-tier journals like Ecological Modeling. He has also authored and edited multiple books with renowned publishers. He has completed 5 major research projects as principal investigator funded by national agencies like ISRO, SAC, and NRSC, and the Ministry of Environment, Forest and Climate Change. Dr. Sharma is an elected and nominated member of several prestigious professional bodies, including the IUCN's Commission on Ecosystem Management and World Commission on Protected Areas. In addition to his academic achievements, Dr. Sharma is deeply committed to capacity building and environmental awareness. He has coordinated over 30 IARS ISRO EduSat-based training programs and has been a key member of several university-level committees. We are truly honored to have him with us today. Let us now welcome Professor L.K. Sharma for his lecture on the topic, Geospatial Technology for Carbon Sequestration.
Thanks to all the coordinators of the GIAN programs for inviting me for this prestigious and world-renowned platform of the GIAN. And I would just like to tell that my topic of today's presentation is the geospatial technology for carbon sequestration. So, as everybody knows about that how the geospatial technology, particularly in the current scenario, is very, very important in terms of not only for the monitoring of the natural resources as well as implementation, strategic development, policy making, and so many other resource utilizations properly, we are using the geospatial technology. And not only for this particular topic is very important for the beginners, this is also very important for the persons who are already involved in different kinds of research, and they may be also benefited for this one, either is irrespective of their domain also. So, this is the way by which we are just elaborating, and today's topic is the geospatial technology for carbon sequestration. Carbon sequestration, everybody knows about that we are facing, or we are in the era of this climate change situation right now. So, in that situation, our hope is totally depends on the natural resources, particularly the green resources actually. Our hope is to how much they are sequestered the carbon which is in the atmosphere floating every day, day by day, or increasing day by day. Due to this one, the climate change phenomena, particularly the temperature rising and so many other phenomena will be also developed, and we are facing lot of the things. Lot of money is wasted in terms of the utilization and in terms of this acclimatization of this particular problems. So, this is the way by which we can, how we can tackle with the use of the geospatial technology, that is main concern in this particular things. Now, you see the things, the whole world is facing severe environmental challenges that require the holistic solutions actually. Air pollution, biodiversity losses, climate change phenomena, natural hazards, food shortage, greenhouse gas emissions, urban heat island effects, water scarcity, water pollutions, habitat loss. All these are the very prominent which you are already aware of all these things. but many of these you may not be aware about this one. So, we will not discuss about all these things, but let us discuss on this particular all these aspects which you are showing here. Air pollutions, due every component of this particular slide is resemble with each and every concern, each and every part of this. Air pollution may be also dealt with the biodiversity loss. Climate change phenomena may you also resemble with all the problems or the scenarios which you are showing here. So, greenhouse gases emissions, particularly you see greenhouse gases emissions. If we are not controlling the greenhouse gases emission, because one side we are going for the developmental activities, we are just creating our a hypothetical world we are just creating, and another side we are facing a lot of problems due to this one. So, how we can tackle all these things, and is this the way any solutions, or is this any of the balancing act by which we can maintain the situation? If it is not so, then what is the solutions and what will be the mechanics, what will be the strategies, what will be the techniques which is right now available by which we can use and we can mitigate the same. No doubt, and very frankly I am telling you, no doubt that we are living in the era where the developmental practices is must right now. We cannot stop the developmental activities, and if the developmental activities is gone, emission will be gone definitely. But how we can minimize? At least we can try for the minimization also. So, in that way, these are the whole things, whole pictures is come out that these are the sources by which we can accumulate that the solution is required for these type of problems in our sustaining our life on this earth particularly. So, the almost, if you go around all these scenarios, particularly one element is creating a very important role. Which one? Which is the carbon itself. So, carbon, most common element found in the living organisms, and it is the basis for the life. So, we cannot live without the carbon actually, but this carbon is also create problems for the human livings. See, this is the actual phenomena that one time we have to require this carbon source in our life to sustain our life on this planet. And the other side is that this is the biggest element which is creating our problems day and every day. So, it means everybody is telling that ati sarvat varjayet, means everything is exceed in amount, which always lead to the catastrophe or the problematic situation. Similar way, if we are not balancing the situation, then it will be create a problem, and that is why we are facing the problems. Situation is not equilibrium or equally situation. Somehow the carbon emission rate is going higher in the side, and the sequestration or the sinking capacity of the other resources is very less. That is why we are facing the problem, simple reason. So, carbon is constantly cycling between the organisms and the atmosphere, and that is the main problem actually. The carbon cycle, constantly cycling between organisms and the atmosphere to the organism and organisms to the atmosphere. The particular cycle of the carbon is problematic, because somehow the intrinsic factors which are responsible for triggering one form to the another form, that is also imbalancing. That is why the problem is arising. Otherwise, nature is have the ability to maintain all these systems very efficiently, but unfortunately this type of situation is not there. That is why we are facing the problems. Forming stable bonds with many elements including itself allows carbon to create the vast majority of the molecules. You know better, our each and every organisms is made by carbon, hydrogen and oxygen, which is the base elements for the human life, and carbon one of them. So, it is essential, but how much and how we can tackle it, that is the challenging role that we are facing. All of you are aware about this one. So, I am not much more emphasis given to the carbon cycle, but if you see the process of this carbon cycle, you see the interconversion in the environment and particularly in the photosynthesis mechanism. You know, the photosynthetic activities right now very degraded due to the sum of the mechanism of the anthropogenic factors and so many other things are there. Even the natural disasters and natural calamities is also responsible for the mechanism disturbing the photosynthesis mechanism in nature itself. So, this is the way by which you can easily understand how the carbon playing an important role in our carbon cycle. Now, the facts, some of the facts you must know about this one, that according to the WRI report, you see in forest 16 billion metric ton per year CO2 will be absorbed. So, it means that our natural resources like forests throughout the world, 16 billion metric ton per year of the carbon dioxide or carbon content absorbed. Whereas, in another scenario, you just see how the atmospheric carbon dioxide concentration 427 ppm is there, and it is rapidly rising. Most of the slides you have seen in your previous lectures, that how the carbon concentration in the atmosphere is rapidly increasing from last century to this coming into the current status. So, now you see the sinking capacity is very less in comparison to the emission capacity. And if you see, one of the record is also saying that the 861 gigatons of the carbons, this is equivalent to the nearly a century's worth of current annual fossil fuel emissions. So, how the drastic changes and drastic situation is there, you just imagine this one. And among this all these 860 gigatons carbon, if you calculate, then the 42% in the living biomass as in the form of above ground biomass and the below ground biomass. Above ground biomass means bole biomass, upper layer of the earth, the biomass which we have calculated, and the below ground biomass means the soil carbon, soil cycle you can say. So, if you aggregate this one, this 42% of the biomass is important role playing in terms of the whole carbon system. This is very important here, because by this way, if you calculate the biomass, you can exactly know that how much of the carbon is stored in our living organisms. And the dry or the bole biomass, you can say this biomass is a living fuel, you can say living fuel for the organisms. So, half of the carbon 50% may be considered as a biomass of the living trees. So, this is the way by which we can easily assume that how much biomass is resemble with the carbon concentration in the carbon cycle particularly. Now, the picture is coming that how the remote sensing or the geospatial technologies is coming important role playing in terms of carbon storage or particularly the carbon sequestrations. You see, the first one part, you see this one is the harvesting methods. Before that this era is generating, we are just how we can calculate the biomass, we are just cutting the trees, dried up, and then we are just going for the biomass production, and we calculate the biomass. But now the situation is totally changed. We have the remote sensing technology by which without harvesting of the particular trees or something living organisms, we are just calculate the biomass, and without touching the object we are creating the information or getting the knowledge in the particularly the estimation of the biomass is possible right now. So, that is very important part in terms of tree height measurement, best of the height measurement, how much the girth of this particular tree is, you can easily monitor, easily maintain, how much of the biomass of a particular area it is possible right now, you can calculate. You can also calculate or estimate biomass in which where the areas is non accessible to the human beings, like the Arunachal Pradesh or any hilly terrain. If any person cannot go to the particular field for the sampling, you can easily take the biomass from that remote sensing technology without going to the field. But definitely for this type of technology, ground sampling is required, definitely. So, with the help of the ground sampling, we can easily estimate the biomass in terms of remote sensing and GIS technology. So, in the traditional forest survey methods, we can use the advantage is that high precision, mature in application and high flexibility, whereas the shortage is that time consuming and labor intensive, highly destructive and limited coverage. That was the primarily objective of the previous methods. But right now, the technologies of the remote sensing has created the whole scenario is changed right now. Extensive coverage, it means the remote sensing provide the large and synoptic coverage of the entire region. High timeliness, exactly no any time dependent mechanism is there. Multiple data sources, you can take different type of the data sets in different time domains also. It means the temporal data set you can also take, that is the advantage. High efficiency, non-invasive and the low cost. So, that is the advantage of the remote sensing technology, by which you can easily mapping of the forest carbon storage distribution, and which is the basis of the particular carbon cycle management. If suppose this is the forest area of a country, and if you monitor, if you evaluate how much biomass is there, then easily you know that this particular country has this much amount of the carbon storage capacity. It means you can manage whole global level carbon cycle, that how much carbon is sinking and how much carbon is emitted there. So, that is the basic mechanism by which you can easily manage the climate change situations, or you can monitor the climate change situation by the use of this technology. Now, I am not going into the primary part of the remote sensing, but very shortly I am just telling that if you categorize the remote sensing, this is two types of the basically remote sensing, active remote sensing and the passive remote sensing. Active means their own source of energy. It means some of the LiDAR, radar, they have the own source of energy. So, they will eliminate the energy and ultimately captured by the sensor. These type of sensor accurately measure the Z perception, X, Y and Z perception. So, Z perception will be also captured by these technologies. But some type of the instrument are also available, which is known as the passive remote sensing, and passive remote sensing means they have not their own source of energy, but they will take the energy from the sun as a source, and they will take the energy and illuminate, and the reflected energy will be captured by the sensors. So, these type of the particularly the remote sensing is there. But the geographic information system, if you added, this is very important for the decision making tools actually. So, decision making if you want to take, then you have to create all the global level data, or the whatever the data set you want, you can create the different layers, and you can segregate one by one objective, one by one objects of the natural surfaces, and you can create the layers, and ultimately you can combine all these images layers, and ultimately you can create the decision making process, by which is a policy level or planner level. If you want to do something, then you can easily create, because lot of data set, lot of information is there, how you will be managed actually. So, for managing of the data set and information, GIS playing a very important and fundamental role in terms of management. Now, types of remote sensing data used for biomass and carbon studies. I already telling multispectral sensors, hyperspectral sensors, all these are the passive sensors, and the active sensors like LiDAR and the radar, all these are the active sensors. So, in the passive and active sensors, you will see different kinds of the sensors which are available, which is widely used for the carbon sequestration or carbon research, or you can say carbon cycle assessment. Active sensors, multispectral like Landsat, Sentinel-2, MODIS, these are the types of the data set you can use. Hyperspectral, very advanced stage of the remote sensing, where Everis-NG, Prisma, Hyperion, all these data sets are available. Hyperspectral means number of particular bands is more, number of bands is more means information is more. So, in multispectral and hyperspectral, if you compare, then the hyperspectral remote sensing is telling that number of continuous, not continuous, contiguous bands. It means the wavelength will be shorter, but the energy will be high, and in terms of the number of bands will be more, and number of bands will be more, it means number of information is more. So, you simply, if you want to understand the situation, hyperspectral data if you are using, then you can categorize or you can easily identify the species level of the demarcation. Means in a tree, in a group of tree, you can easily identify the mango tree, you can easily identify the Ashoka tree, you can identify the different kinds of the trees. So, that is very fantastic tool by which you can, from satellite data, you can easily segregate the species level demarcation. That is a fantastic tool by which you can use the hyperspectral data. In passive sensors, microwave remote sensing is basically used for those areas where the climatic situation is not very favorable, like the rainy season, like the hazy season, like in the day and night images if you want to take, then it is a very fantastic tool by which the microwave remote sensing is provide a solution that you can take the day and night images, no any effect you can see, and you can take the images in terms of any type of the hazy situations or any type of the weather situations. So, in the hilly areas, particularly hilly terrain, if you want to take the images for the biomass estimation, you can easily take and you can easily calculate. So, no any boundaries, no any limitation is there. So, these are the passive sensor. LiDAR is also a very fantastic tool right now. You can create the 3D image of any type of the surface with the jet perceptions, and ultimately you can create the bole biomass and all the biomass you can calculate, height you can calculate. So, these are the techniques by which, and all these techniques are based on basically the spectrum. These are the spectrum by which you can easily understand that these are the basic of the remote sensing. Now, I am coming to the part that some of the case studies by which you can easily understand that how the carbon sequestration and the remote sensing are jointly linked together, and how you can understand this one. For the determination of the gross primary productivity, what is productivity? Productivity, primary productivity is production of biomass per unit area per unit time, that is known as primary productivity. So, particularly the primary productivity is very resemble with the gross primary productions, biomass productions, respirations, and all these oxygenated activities in the particularly ecosystem level. So, when you know about the primary productivity, if you want to know how much the global level biodiversity is there, what is the production level is there, biomass level is there, then you need the gross primary productivity, and gross primary productivity is, if you minus the respiration part, then you can easily calculate the net primary productivity. So, if you want to derive the net primary productivity, you have to tackle the gross primary productivity and the respirations in a particular ecosystem. So, in ecosystem modeling, you can use the remote sensing data, different MODIS type of the data set. If you want to take the global level mechanism, if you want to apply, MODIS data is available free of cost. You can download the MODIS and you can easily go through this. Some of the procedures are already available, but this is the one of the case study by which you can easily understand that in the Karnataka state, this is the Western Ghat region, and particularly on the basis of the remote sensing and GIS technique, different data set they have taken, and ultimately this study is showing that the particular zonation mapping of the monsoon level and the state biodiversity boundaries and district boundaries, so many different kind of aspects you can easily compare. And by this experiment, you can easily that in 2003, you see this is the in the July month, July, August, June and September, you see this one particularly, this graph is showing the ambiguities, the GPP will be determine this one. The graph is looking like this one. But you see in the next graph, this is the 2003, and now you see this is the graph which we have generated GPP modeling for this particularly continuously up to 2020-21. And you see in the same region, the frequency of this particular GPP in time interval will be very, very disturbed. This is showing that how the climatic change scenario is going on, and particularly in the period of the 2003 to 2021, if you see the particular period of this month actually, temporal data sets, you can easily understand that how much peaks are there. It means some type of the GPP of the global level is also disturbing right now. So, from past to present, you can easily understand that how much of the fluctuation in the GPP is occurred, or you can estimate by the use of this particular technique. You see this one, those 2003 to 2021, this is a carbon storage mapping, and you can, this is the example by which you can easily understand that how the remote sensing or geoinformatics or geospatial technologies playing an important role to determine the carbon storage, particularly in terms of the temporal type of the resolutions. Now, you just one of the another example that the multispectral and hyperspectral data for forest biomass estimation. This study was carried out in the Shulpaneshwar Wildlife Sanctuary in Gujarat, and you see we have taken the particularly the vegetation indices we have created, and sample methods in the field inventory data in the traditional approach we have also created for the validation of the data. So, we have go into the field, ultimately we have designed the sample plot, taken one by one plot, designing, sampling, designing, creating the tree height, tree diameter, density and the specific gravity, and ultimately we have created the biomass for the particular applications in a particular field area. And then this particular point we have just uploaded, or you can see the particularly resemblance with the satellite data also. And then whole particularly the one of the century we have created the biomass model. So, this is the way by which another example by which we can generate the biomass or above ground biomass modeling. And you see different indices are also there. On the basis of this one, we can easily eliminate the different classes, that which type of the classes, what is the biomass density is occur there in the particular sanctuary areas. Now, the question is coming that how the calculate biomass and the earned carbon credits. So, in terms of this one important phenomena is coming out, that the nature based solutions. Right now, nature based solutions providing a better solution for each and every aspect in terms of the remediations, adaptation of the climate change situations, as well as the carbon sink and source capacity development. And it is widely and worldwidely accepted model, the nature based solution, because it is simply saying that nature itself healing capacity of all these type of the degradations or all these type of the hazards is coming. So, this is the basis for this one, and actually it is providing the restoration capacity by which we can, which is degraded land or degraded ecosystem is there, we can also generate the different type of mechanism by which we can understand that nature itself providing a sufficient role for regeneration capacity or restoration capacity itself. So, in that particular case, nature based solutions actions to address societal challenges, so the protection, sustainable management and restoration of ecosystems benefiting both biodiversity and human well-beings. So, it is a nature based solution, and this nature based solutions for Indian continent, I can easily say that we have practices the nature based solutions in our own life cycle, even our own cultural practices, our different type of the daily routine practices, we are already adopting this one. So, no one can directly dictate us that yes, this is the new term for us, because this is not new term. We Indians know that how the nature it is sustaining the nature based solutions, and we are simply we are practicing in our daily life also. So, this is the way by which we can also generate the thoughts for the carbon cycle sequestration, carbon cycle management practices. Nature based solutions term introduced by World Bank in 2000 later and championed by International Union IUCN. It is IUCN based mechanism firstly given, and it is also included the climate change mitigation and adaptation, disaster risk reduction, economical and social development, human health, food security, water security, environmental degradation and biodiversity loss. So, all these parameters you see which we are equally dealing in terms of the nature based solutions, and so many aspects, so many organizations already working, and definitely we are doing a good job in terms of the adaptation mechanism for the nature based solutions. And you see this is the Jordan and Foils created 2022, the image is showing itself that firstly we are given the term nature based infrastructure in first stage from 2006 to 2015. After that we are coming in the phase of the green infrastructure. Again we are coming to the ecosystem based adaptation, ecosystem based mitigation. Now NBS comes in the effect of the 20, after that you see in 2014 to 15 we are just coming in the phase of this nature based solutions perfectly, and after that now we are coming into the nature based infrastructure and nature based features. So, now this is the well adapted mechanism right now NBS as per the United Nations policy framework. Now, I am coming to the different type of the carbons. You may be heard about different type of the carbons, maybe you are familiar with this one, but in a very simplest way I am just telling that three type of the carbon is the monster of the carbons you can say, and three type of the carbon is the safeguard of the human life. So, one thing is the bad carbon, one thing is the good carbon you can categorize. And how we can categorize? A very simplistic way I am just telling that the red carbon, teal carbon, green carbon, brown carbon, blue carbon, black carbon. No anywhere this type of segregation is there, but depending on the behavior of the production of the carbon, emission of the carbon or sequestration of the carbon, cycling in the nature, we can categorize a different type of their properties actually. This is bad or this is good for the organisms or the human life or the environment. So, you can categorize this green carbon, green signal always green. So, it means the plant based carbon. So, this is the carbon which is very good in the form of greenery or the plants, they are producing this type of carbons. So, ultimately this is the green carbon is good carbon. Blue carbon, the oceans always creating the trapping mechanism for the carbon. So, this is also the good carbon. Teal carbon, it is a new term, and it is also coming for the mechanism of the trapping of the bed carbon mechanism. So, it is also a good carbon, and it is providing only in the inland wetlands. So, wetland is very important right now. So, where we can tell that the wetland is very important? Wetland, because the teal carbon inland freshwater wetlands, these are the major source of this teal carbon particularly, and this type of the carbon is known as a good carbon, you can say. But which is the monster of this carbon, or all this world is troubling for which type of carbons? Basically the red carbons. Where the red carbons? Any among of you know about the red carbons? Those who are working in the glaciers, or those who are working in the snow regions or hilly altitude, particularly in snow regions, the chemical reactions may produce the red carbon actually, due to the microorganism productions is there, and due to the microorganisms and chemical productions, the carbon which is stored in the ice crystals, they are looking like as a red color actually. So, this type of carbon is red carbon, and this red carbon is right now very prominently threatening to the upper regions, or the Himalayan regions, or the Arctic regions, or you can say the glacialic studies particularly. This type of red carbon is a threatening situation right now. So, this type of carbon is very bad carbons particularly. Black carbons, everybody knows about the vehicular pollutions or all these things, the chimneys of the factories, and they are emitting the carbon. This type of carbon is known as black carbon. Brown carbon, it is also coming from the industries basically. So, the pollution which is created by the different kinds of the chimneys, particularly SO2 and different in combination with the different pollutions, this type of carbons is known as the brown carbon. So, these are the major type of the spectrum you can generate by this one, and this is the spectrum of the carbon. Now, you see that this is the red carbon, a common pigment produced by snow microorganisms and all living biological particles on snow and ice that reduce albedos to survive, absorb abundant green and blue wavelength of the light melting the snow and ice. This is the red carbon. Black and brown carbon, this is the both are the produced through the incomplete combustion of the organic matter. It also reduces snow and ice albedo, 50 times more light absorption capacity and 10 times more mass than the brown carbon. Natural, such as during wildfires, fossil fuel burning and industrial activities are also major source of this type of carbons. So, ultimately you can easily categorize this type of carbon is the black carbon, brown carbon, or the red carbon. These are the all these problems are created by this type of carbons is known as red, black and brown. Now, again the second phase of this carbon is that the green carbon, carbon sequestered by the terrestrial forest and the grassland ecosystem, that is the green carbon. It means I am already telling nature itself providing the sustainability, sustaining the nature itself. They have the possibility that one time it is increasing, one time it is also reducing. So, nature is providing their balancing situation, but due to the some of the anthropogenic activities and some of the pressure of the anthropogenic system, actually the human beings are responsible for disturbing this equilibrium, and that is why all the problems are arising. Again the blue carbons, carbon sequestered in the coastal and marine ecosystems like mangroves, salt marshes and the sea grasses, that is also the blue carbon. Now, another term is the teal carbon. This is recently entered the carbon color, this is the teal, related to the carbon stored in the inland freshwater wetlands. Just try to understand, I am just telling inland freshwater wetlands, not all wetlands, inland freshwater wetlands, that comes under the teal carbon ecosystem. What is the significance of the particular teal carbon ecosystem? Habitat of several endemic flora, very large amount of stored carbon, purification of the inland waters, water recharge zone, mitigation of urban flooding, mitigation of urban heat island, and climate change adaptation. That is the main component, main emphasis which is derived from the teal carbon ecosystem. Why this is important? Because this particularly carbon system present in the inland freshwater wetlands, that is more important in terms of water recharge zone potential and mitigation of the urban flooding, mitigation of the heat island effect, climate change adaptations, and all these things are very, very prominent in terms of the particular one type of the carbon system. That is why it is very important. And fortunately, I am telling that this is the very, very throughout the world extremely fragile ecosystems. If you say this is the ecosystem, this is world fragile, most fragile ecosystem right now. Concept of the teal carbon, which was coined by the Amanda and Nihalik and MS Fennessy in 2016, and their paper, one of the paper was published in the Nature Communication itself, and on the basis of this, the one of the Guardian wetland classification in 1979, it was already published, and the term was reintroduced by the Amanda Nihalik in their paper directly. They have in the global level, if you see, they are divided the wetland in their Guardian classification system in the three particularly: lacustrine means the associated with the lakes, riverine along rivers and the streams, and the palestrines meaning the marshy areas. So, they are describing these three type of the mechanism. But on the basis of the Guardian classification, the Ramsar wetland classification, we have taken the broad criteria which has the inland freshwater wetland area full of vegetation. This picture is showing the this one, Kevladev National Park in Rajasthan, and the similar way this is also the Sambar Lake, which is the saline wetlands. And you see the specific criteria, we have decided that non-tidal freshwater or inland saline wetlands with vegetation cover more than 25% under shallow water depth, which is 1 meter conditions, that comes under the this one, inland wetlands. Now, on the basis of this one, different K classifiers we have identified, and the major category we have decided only the palestrine, riverine, and the lacustrines. And ultimately, the teal carbon ecosystems, if we categorize, then again we have categorized in the emergent wetland ecosystem, scrub dominated, forested wetlands, farm wetland, open water pond or aquatic beds. On the basis of this one, the different type of the Ramsar wetland category code, NWCA wetland code, and the US FWS codes we have categorized. So, ultimately the meaning of this slide is that we have created the teal carbon ecosystems in the different 4 emerging zones, where we found that the forested wetlands is a major concern of the particular interest. Why? I am telling to you. Now, the teal carbon stored in the inland freshwater wetland ecosystem, shallow and non-tidal ecosystem, inland freshwater swamp, inland freshwater forested wetlands, inland freshwater marshes, and others. That is the combination of the particularly the teal carbon, and particularly this one, inland freshwater forested wetlands, that is very, very prominent in terms of the whole approach of this teal carbon. Why? Because if we are categorized role of forested wetlands in urban environment particularly, then you see urban green space habitat, biodiversity conservation, urban cooling island, fresh flood mitigation, air purification and water purification. These type of the mechanism, it is a concept by which a society or any type of the inland freshwater forested wetland is there, they will create this type of the positive phenomena in the particular environment. It means this particular till carbon of the forested wetland ecosystem present create a very, very fantastic tool to minimize the climate change effect. And for this purpose, we have taken a very, very simplistic and pilot study for this one. We have taken the area of this, particularly the in Rajasthan, Bharatpur, Ghana sanctuary, and we have taken the area of this one, NDVI we have taken. You see the high vegetation part and the KNP boundaries, you can see Kevladev National Park. For that particular wetland ecosystem establishment, how they are creating this one. This is the, and this wetland is in bad shape right now because it comes under the Montrex protocol. Montrex protocol, which protocol where you can say the wetland has a degraded wetland right now. So, this is not in the a well functioning wetland, but it is a degraded wetland system and it comes under the wetland or Montrex protocol right now. These are some of the species where we found there and very well maintained, and their biomass we have also calculated in the particular areas. And you see the finding is showing that biomass of this particular area is 284 tons per hectare. Carbon stock dry weight tons per hectare, if you calculate with the biomass as per the IPCC guidelines, then the biomass into 0.47, if you multiply it, then you can get the carbon stock dry weight. And we find out that carbon stock is 134 tons per hectare of this particular area. That is equivalent to the 1041 tons CO2 is equivalent to the per hectare. And one carbon credit is 1 ton carbon into 3.67 carbon dioxide equivalent. So, ultimately this is the formula which is already given by the IPCC. So, we have just calculated, and the ultimate finding is that 134 carbon credits per hectare, which is equivalent to the 2010 rupees per hectare, that is the carbon credit of a particular area we have calculated. And again we are going for the same area for the soil organic carbon in the below ground biomass, you can say in 602 tons CO2 equivalent per hectare, 165 carbon credits per hectare, and that is equivalent to the 2475 rupees per hectare. So, if you calculate this one, then if you compare this one, then here 2010 rupees per hectare carbon credits earned, and here 2475 rupees per hectare carbon credits earned. It means the soil has much more efficiency to capture or the carbon sequestration capacity in terms of the others. So, this is not a very big study, we have a pilot study we have done, but this is the very, very preliminary results we have find out, and very fantastic results we have find out this one. So, ultimately the total till carbon credits in the Kevladev National Park, if you see, that is equivalent to the $52 per hectare if you convert, and in the carbon credits 299, almost 300 carbon credits per hectare we have to generate in the particular till carbon ecosystem. This is the story of this particular very small area by which I am just telling to you. Now, the greenhouse gas emissions, particularly emission wise, if you see this study, major challenges for the till carbon ecosystem to be NBS, nature based solutions, if we want to take, then the global methane emissions we have to understand at first. You know, methane is a very, very primary source for this type of the emittive atmosphere environment in terms of the wetland ecosystems. If they are degraded, if they are destroyed, or if they are polluted by some regions, then it may be created a source, great source of the carbon emission actually. So, methane estimated 60% of the total methane emissions are the result of the human activities. That is well known fact. The largest source of methane are the agriculture, fossil fuels, and the decomposition of the landfill waste. That is also a well known fact right now, because every country has a very significant amount of the methane emission, and right now the public or the people, researchers also very much interested about the methane research, methane emission research. Why? Because this is more polluted, more hazardous rather than the others also. I am not telling that others one is not effectively playing a role, but methane is also a very important role playing in that way. Natural processes account for 40% of the methane emissions, with wetlands being the largest natural source as per the NASA record. So, this is the well known fact, some of the fact is there. This is the picture we have taken from the global data set, that you see how much the greenhouse gas emissions as per the 2022 record. You see the methane emissions by the data set, and most of the China and the USA are the leading countries by which you can say they are creating the greenhouse gas emissions, very majorly role playing in terms of the methane also. Again, how we can synchronize or created the link between the geoinformatics to this type of particular studies. Then methane emission in the Kevaladi National Park, we have taken the Sentinel 5P satellite data, that is MERIS data particularly, and you see throughout the year we have taken the data from the methane concentration, and you see this area is highlighted because this area is highly anthropogenic areas, where the human activities was very high. So, in that particular, in the methane concentration, if you see in the March 2024, that was 1931, and if you see in the 2023 image, then if you see 2023 image concentration in the April, you see the same area is also resembled with the highly anthropogenic activities due to the methane. So, this is the way by which we can easily understand. Now, the factors associated with the methane emissions like water, temperature and the vegetation. And similarly, if you find out this one, the methane concentration in the upper region, same way we find out that the LST was also high, as well as the methane concentration was very high in the same way. So, this is the study which is preliminary showing in the result, but it is showing a very important role of the teal carbon, particularly in terms of global climate mitigation, effect mitigations, and particularly the things is very important. So, natural wetland emissions, role of biochar. Again, we have taken a very pilot study that how the biochar is. I think you must aware about the biochar, because last 3 days sir is already telling the biochar, what is biochar and all these things. So, I am not going to the detail of this one, but role of the biochar as a natural based solutions, nature based solution to mitigate the wetland emission, that is also a very important features. Natural biochar, nature based solution, if any nature based solution is there and mitigate the climate change effect, that is a very good phenomena in terms of the mitigation or the climate change effect analysis. How we can do? You see the biochar is there, and if the biochar nature based solution, nature based providing solution is there, we have conducted a seminar, we have used for this Lycor trace gas analyzers. You see, this is a instrument by which you can easily get the methane concentration at a time at a spot. So, we have these are the spectra we have generated for the methane, CO2, H2O. This is the Lycor instrument by which you can easily get the at a time you can get the all these methane emissions, because so many, if you use the different other methods, maybe the lack of accuracy, maybe the human errors, or maybe the another leakage of the gases that may deteriorate the results. So, the perfectly accuracy assessment, we have taken this Lycor experiment, and you see we have taken the 2 sites in the Central University of Rajasthan, where the pond area is there, and this is the some of the smaller wetlands, and we have taken the 2 of the sites. Some of the sites we have taken for the plot design analysis here, and you see this is the way by which we can easily estimate this one. This is a instrument by which some of the centimeters or meters you can say, this is the way by which we can easily measure the methane emission reading, and very light instrument is there. So, and in result you see when the result was analysis, surprising fact we are find out, it is very preliminary, but I am not saying that it is a overall result of all these type of the conclusion, but this is a primary study I am telling. You see 1 hour experiment we have taken 2275.37, see, and 2740 methane concentration was recorded, and inside a 24 hours experiment 2282 and 2251. It means natural emission and the emission after the biochar addition. We have two sites we have taken, one is the with biochar and another one is the not behind the biochar, and biochar made up by the nature based some of the tree materials we have just taken for this one, and the result is showing this one, and in the site 2 2166 ppm and 2129, it was showing that some of the degradation is there. So, it is clear cut indication. I am not telling that this is a good research work for the publication or something like that, but this is a indicative research you can say. If we get more research do in the particular type of the experiment, then definitely we can get more result, more good quality of research work is needed, but this is the way by which we can get the results. So, major takeaway is that the remote sensing and GIS are promising tool for the carbon studies. In teal carbon ecosystems, availability of water, vegetation and land surface temperature have a considerable effect on the atmospheric methane concentration. This methane emission is the major limitation of the teal carbon ecosystem to be an nature based solution. So, the proper management of these highly vulnerable ecosystems can be a solution for the methane flux management. Development of teal carbon zones should be promoted for the sustainable urban planning. Natural teal carbon flux mitigation approaches like biochar addition must be studied under natural conditions to minimize the emission. And this is the paper we have already submitted to the Stoughton right now, and the floor is open for regional global research collaborations or funding opportunities in the following domains, particularly the advanced remote sensing database or software, geospatial modeling of greenhouse gas emissions, greenhouse gas mitigation approaches using biochar, and the development of teal carbon zones. So, some of the areas we have already developed. Recently, one of our book is already published by the Springer, is a author book, and this is the case study which was published by the Hindu. India's first teal carbon study bets on the wetland to address the challenges of climate adaptation and resilience, and so many. This is another book of mine that which we are dealing on the Aravalis and all these things. This is our research team. Thank you so much. Yes, please.
So, this is very interesting thought, and can be very impactful if you see some more data and how it works. I am just curious to know that how did you apply biochar? Was it sprayed in the pond or how?
No sir, biochar was actually we have just created the biochar. I am not in the expert in the particular biochar. So, one of my colleague Dr. Bhagwan is prepared the biochar actually, and some of the pyrolytic process or whatever the scene is there.
No, how it was on the site? At the
site was that we just sprayed the biomass on the water table at that
Biochar on the surface.
on the
Yeah,
surface.
that's my point. Yeah.
Biochar on the surface, we have just sprayed. So one site was the sprayed of the biochar on the surface, and one charge without the biochar. Maybe some mixing of the water is also
that's
there,
fine, yeah.
but we have just, this is a preliminary work we have just done.
That's interesting idea. I was just not sure how.
I am
you-
not expert in the particularly the biochar, how we are using,
No
but
worry.
somehow we are just helping with the Bhagwan and then his team, and particularly he is working in the biochar and all these things. So we just initiated this one.
Yeah, it's really
But
interesting.
result was very, very unique at that
Yeah,
time.
it's really interesting, and I would like to see how we can do this together further.
Sure, sir,
Thank
sure.
you.
Thank you, sir.
Any other questions from the audience?
Thank you, sir. Thank you for the nice presentation. I think I have one correction to mention on the active and passive sensors. I think there is some spelling mistake. The
Okay, no problem. This is a human error, but main thing is that one source of energy, that is the active source, active sensors.
yeah.
So this is a simple way. Maybe the slide, maybe some typographic or so many errors are there, maybe, but this is the okay for this one. For understanding, I have just already cleared that this is the way. By
Yeah.
Hello. I can see those results. I think those could be measured within the chamber. If you do in actually ambient condition, there is lots of AD covariance and some other interferences are there. So in that condition, you need a phase chamber. Then only you can measure in ambient conditions. Second point is that when we go to apply biochar in open fields, one most important thing is that it's not just chemistry. Then there is lots of involvement of the microbes. So once it will be submerged, then there are many such methogenic activity could be enhanced or maybe changed, and you will have a similar situation like we get it lots of methane emission from peatlands or rice fields. So that must be considered when you apply that.
Definitely, this is a preliminary study, but this is the best scope for the biotechnologist, best scope for the microbiologist or algologist or whatever the things they can develop, because a lot of options are available right now. Maybe the interaction between the microbes, what is the mechanical situation, what is the chemical situations, a lot of chemists can do different type of the biochars. So many other applications may be derived from this one. So this is the basic fundamental way by which we can do. Even though remote sensing we are just doing with this very well played for the larger domain, but the definitely it's a wider scope which the study is providing, that if any person who is doing this type of things in a very single area or a very specific area for the better result analysis, then definitely they have to carry out the chamber based analysis or so many other things is to be applied actually.
Sir, sir,
Yes.
sir, very nice presentation. And like I would like to know how you are integrating remote sensing to study this particular phenomena of biochar and application of biochar.
Actually, I have already in our previous slide, you were not present there that time, but I have already shown that different kinds of the remote sensing techniques are available right now, like the hyperspectral remote sensing. On the basis of the particular spectra or the molecule of the particular spectra, we can generate the spectral libraries, and the spectral libraries will tell you that which type of the chemical constraints and which type of the flavonoids, whatever the another alkaloids are there, different chemical constraints are there. So on the basis of this one, we can similarly use for the GCMS analysis or all these things. we can similarly use for the different type of the spectral analysis for this one. And ultimately, because this is the era for the interdisciplinary research work. So, each and every aspect we have to conclude, because this is not a single phenomena by which we are doing it, this is the input and the output will be there. This is a global phenomena by which each and every person's their role can play and they can do better. So, remote sensing for the larger domain area, definitely no any technique without remote sensing can be applicable. But if you want to do a point study or the very case study for the particular location study, then definitely it required the lot of lab work is required.
Thank you, sir.
Yeah, please.
Hello sir, I am Vartika Tripathi. Sir, I want to ask from the slides. Sir, which color of carbon is more impactful on our earth, sir, climate?
On our earth?
Earth climate, sir.
Earth's climate?
Yes, sir.
Definitely it is a black carbon.
Black carbon, sir?
Yes.
Okay.
It is a black carbon.
Okay. Since we are running out of time, so we can take the next question.
Why I am telling black carbon? Because each and every time when you see the forest fire, wildfire is there. So wildfire source is the black and brown carbons basically. So, and vehicular pollutions, emissions majorly, and the industrial pollutions majorly, the black carbon is emitted. So, this is the very foremost, but definitely carbon is always positive side and negative side is also there, and only the whole the play is only about the balancing of this one. So, I am already telling that if the balance is disturbed, everything will be disturbed. So, whole thing is on the balancing, how we can take the balancing situation, but unfortunately we cannot stop our developmental practices, and development, if you want to do the developmental practices, then we have to sacrifice in terms of the carbon emission or so many things.
Okay.
Anything? Thank you.
If anyone is having any questions, they can mail to sir on the following mail ID. Thank you, sir, for your talk. The integration of GIS and remote sensing will significantly augment the lab research for biochar production. And with that, we now come to the final segment of the GIAN program, the valedictory ceremony. It has been a remarkable journey filled with knowledge sharing, and we are truly grateful to everyone to making this program a success. To begin the valedictory program, I now invite Dr. Garima Kaushik, course coordinator, to share summary of the 5-day GIAN course.
Once again, a very good afternoon to each one of you. It is an immense pleasure for me to welcome you all to the valedictory session of this 5-day GIAN program on renewable carbon and fuels from organic waste, which we have been running from the past 5 days. And ऐसा लगता है जैसे कल ही की बात है, हमने ये academic journey शुरू की थी और आज इसका समापन भी आ गया. So, बहुत ही मतलब ऐसा ये गैदरिंग के साथ इतना माहौल बन गया था कि लग नहीं रहा कि आज इसको हम ख़त्म करें, but we have to proceed with valedictory. So, with this, it is an incredible opportunity to engage in the cutting edge ideas and deepen our understanding with our resource person, and hence I would once again welcome Professor Sandeep Kumar sir from ODU University, USA for this valedictory session, and truly enriched us in this course program throughout this entire journey. And we are grateful for bringing not only national solutions to the national and local problems, but also giving a global perspective to the issue. I also take this opportunity to welcome all the dignitaries present in this hall. Professor Rajesh Kumar, Head of the Department, Dr. L.K. Sharma, Dean of the school, Dr. Devesh Sharma, and our faculty colleagues, staff members, ICT cell and everyone, and all the participants from outside this university, as well as PhD scholars, students from our programs. I welcome you all to this valedictory session. And as we gather here, reflect our learning and celebrate this successful completion of this academic journey, let us watch a small video on this occasion. And with this, after watching this video, we would be eager to hear your feedback, your experiences, and take away notes for further progressive improvement.
Thank you, ma'am, and thank you, coordinators, for making such a wonderful video. I now invite our dignitaries, Head, Department of Environmental Science, Professor L.K. Sir, Professor Rajesh Kumar, Professor Sandeep Kumar, Dean Devesh Sir, and Coordinator of the program, Dr. D. Bhagwan, to please grace the dais. We now request Professor Lakshmi Kant Sharma, Head of the Department, Environmental Science, to share a few words about the program.
Good afternoon to everybody. All of you are, I think you must enjoyed all the sessions of this GIAN program. And since starting for this program, Professor Sandeep Kumar given a very fruitful sessions to you, and you must learn about a lot of things in terms of their specialization. particularly the exposure to the foreign universities, to the Indian students and the Indian researchers. This GIAN program is organized, and Government of India is funded through this program only for the interactions, what type of the new technology is coming, new methods is developed in the different domains, and particularly the interactions with the Indian students, that and Indian community, research community particularly. So this type of the programs is organized. The value addition is that if we are learning, if we are creating our own strength or develop our strength in the particular domain, and we have learned lot of things from the expert, that is the value addition. And I think you must have developed your own skills through this 5 days program through the GIAN. And I think your stay was pleasant in this university. I think all the arrangements made by the organizers, Dr. Garima Kaushik and Dr. Bhagwan, has well managed. So it was startingly, we are just thinking that Dr. Bhagwan is very much thinking about that how we can do this type of things and how we can successfully manage all these activities. But I think I can say that this program is very successful, and on behalf of the Department of Environmental Science, I can say that entire faculty were involved, active involved in the particular program, and definitely our scholars, our students, there are a lot of work done in the particular successful event organizations. So I congratulate all of you for this one, and in future definitely we will organize similar kinds of programs, and definitely our motto is to enhance your ability, strengthen your knowledge in your particular domain. That is our main motto, and definitely we will continuously going on in that way. Thank you so much.
Thank you, sir. I now invite Dean, School of Earth Sciences, Dr. Devesh Sharma, to address the gathering.
Good afternoon, everyone. So I think today is our last session, but this is the beginning of new journey, because 1 day and 2 days is not enough, but 5 days are enough to start a new journey. So my sincere thanks goes to Professor Sandeep Kumar for his valuable timing, because he spent 5 days with you, and more important is the interaction, because audience and participants are more important for any speaker. So thanks to all the audience. I started with you first, because audience are the important part of any training, and definitely Sandeep sir is now, I was talking to him that for these 5 days, like we were there looking like 1 hour before we started opening ceremony, but now it is 5 days. But definitely we will take it forward, and how we can develop our relationship with not only the organization, but how we can come up with some kind of collaborative proposal and projects also. So that's, we are looking forward for this, sir. And second thing is, thanks to coordinator, both the coordinator Dr. D. Bhagwan and Dr. Garima Kaushik, because I am looking from last 1 month they are involving various activities and coordinating with each and every team members also in a very smooth way. That is a kind of learning for all the new members also. So how to create this kind of environment so that we can run a program. Thanks to Professor Rajesh Kumar, because he is not only the professor in the department, he is IQC director also. So this will add the university, some activity in the university also, and it will enhance the ranking and other systems. So I think Professor Rajesh Kumar will share his view on that. And thanks to all the colleagues of the school and other students and PhD scholars for their contribution. And topic is really an interesting one, but definitely 5 days are not enough, so you have to take it forward in some form, right? Whether your master thesis or in kind of some other PhD research work and all this. So thank you very much.
Thank you, sir. I now invite IQAC Director, Professor Rajesh Kumar, Department of Environmental Science, to share his views.
My friend Sandeep ji, it's our pleasure that you are here. जो हम हिंदी में कहते हैं 7 समंदर पार से मेरा मित्र आया है और आकर के 1 हफ्ते तक मुझे रोशन किया है. बहुत बहुत धन्यवाद, साधुवाद. Dean, School of Earth Sciences on the dais, Head of Department, Professor Lakshmikant Sharma on the dais, the Coordinator, Dr. D. Bhagwan on the dais, the Coordinator, Dr. Garima Kaushik off the dais, my faculty members, senior members like Kamle sir, Ritu madam, Subrat Panda sir, Shailesh Patidar sir, and few members are missing, but I still address them also from here. And wonderful audience. We have spent 5 days with our external guest speaker. I have been given a task to say a few words as a closing remarks. It is really a very difficult task to say closing for a topic that says something. The name is what? Global Initiatives for Academic Network. Initiatives always says about the beginning, and the beginning is not a small, global, and the global beginning will take time to even mature, and before getting maturity, I can't say this is a closing remarks from my side. This is basically a beginning remarks that this network should strengthen further and further as per it has been visioned by the Government of India and every others. Also, this has another word. If you take this into the Hindi literal meaning, GIAN. GIAN has a meaning of knowledge. When you're talking about the knowledge, if you can say closing remarks for the knowledge, it's again a very difficult task. I can't say this. So again, this knowledge need to be spread and spread and spread. So it's a beginning of spreading the knowledge, and knowledge amalgamated with the experts from the different countries should further enhance. This is the remarks from my side. Coming further, looking at the faces of the audience, if you are happy, this says the success story, that the program of 5 days was really wonderful. And this would have been wonderful. Why? Because I would have been fortunate to select a wonderful guest, wonderful teacher, wonderful friends, because he has delivered his talk not only as a teacher, not only as an expert, faculty from the ODU, rather than as a friend, because I could see the photographs and mixing each other together, and your interaction going to the another, which university, Sikkim, Manipal probably, you went over there, so I saw the photograph. I witnessed first day and I'm witnessing the last day. So in between, your faces are saying me the story. Based on those stories, I am really appraising this all activities that has been taken care over here. And as I am saying, this is the beginning. So in future, we shall be having another program of this kind, or any other branches of this kind of program, where we can again gather the students, faculty members from the different parts of India, and we could be the host. Being host sometimes gives great pleasure. So I'm a part-time of the host. Major host is our 2 coordinators. But even if you are associated with the host, it's a pleasure. And being running a program in your university, it is always a pleasure that we are getting some name and fame and outcomes. And the purpose for which the university is to share the knowledge. So we have taken this initiative to share the knowledge from abroad. If you all have to go over there and take this knowledge from the ODU, probably it will be very cost expensive, so none of you would have preferred to go over there. and this has been made so simple with the funding agencies of the Government of India. So my sincere thanks to the funding agencies and the organizers who has put pain in formulating the proposal and jointly discussing with our experts over there, and finally it has been successfully completed over here. So it goes to the credit of everyone, including the first credit goes to the participations and whosoever has come from the outside of the Central University of Rajasthan, a special thanks for them. And with all this, I'm giving thanks to everyone, and thank you for giving me the opportunity to talk to all of you. Thank you.
Thank you, sir. We now invite a distinguished speaker of the course, Professor Sandeep Kumar from Old Dominion University, USA, to share his feedback on the program.
First of all, thank you everyone. और मैं 5 दिन से इंग्लिश बोला हूँ, so I'll go out Hindi, okay? Okay, because it's like home for me. So, thank you. It has started with Dr. Bhagwan. नेटवर्किंग का पावर मैं बता रहा हूँ. हैदराबाद में मिला अनदर ज्ञान प्रोग्राम. डॉक्टर भगवान से मिला, फिर आपसे मिला थ्रू कोऑर्डिनेटर. नाउ कितने लोगों से मिला आप देख लो. इन डिपार्टमेंट चेयर एंड फ्रॉम माय होम टाउन, ओके. और आप लोग 50, मे बी मोर देन 50, एंड इंटायर डिपार्टमेंट फैकल्टी. अभी मैं डॉक्टर कामले से बात कर रहा था, मुझे लगा ही नहीं कि कोई एक ऑर्गेनाइजर है इस ज्ञान का, एक कोऑर्डिनेटर है, 2 कोऑर्डिनेटर है. पूरा डिपार्टमेंट एंड कॉलेज बहुत फर्मली खड़ा है इसके पीछे और वेरी वेरी इन्वॉल्व. एंड जहाँ तक मेरा एक्सपीरियंस है, पधारो मारो देश सुना था राजस्थान, मैं उसमें ऐड ही करूँगा, कम नहीं. मुझे बहुत ही अच्छा अनुभव हुआ. इनसाइड द कैंपस, होटल, आउटसाइड, कल जयपुर की मणिपाल टूर एंड ऑल इज फैंटास्टिक. ये सारे कॉम्बिनेशन में एक दूसरे को जानने का काफ़ी टाइम मिला. कई साइड मीटिंग्स किया हमने, पीएचडी स्कॉलर से अलग से बात करने का चांस मिला. काफ़ी एनर्जी है, एंड आई विल से ऑल ऑफ यू आर वर्किंग इन राइट डायरेक्शन. डोंट मैटर यू वर्क, यूएस जाते हैं, कनाडा जाते हैं, यहाँ. So we have one planet and you are in supporting that planet, so we can work from anywhere, ठीक है. और आपको मुझे इतने लोग मिले और कितने नेटवर्क और मिले यहाँ से. सेम थिंग, मैं वहाँ जा रहा हूँ तो आपका एक स्पोक्समैन मिला उधर. आपको कोई भी ज़रूरत हो, मेरे लैब से नहीं भी होगा बियॉन्ड, देन आई कैन बी ए मेडिएटर और फैसिलिटेटर और कनेक्टर. ओके, सो दिस इज़ व्हाट ज्ञान प्रोग्राम. So this is what GIAN program meant for, global initiative for academic network. And network we built so much from CU Raj, from other institution, other CU institution, and many faculty, students and everything. So keep building and always should have follow up. If we finish here, then another GIAN program then is not done. Okay, so what we built it, let's cherish and pursue on that. With that, thank you once again, and I really enjoyed. और मुझे लगा नहीं कि अभी जाना है 1 घंटे में. Okay, thank you. और मैं कुछ यहाँ ब्रोशर रखा हूँ, आप जाते समय ले सकते हो. डिपार्टमेंट के कुछ प्रोग्राम्स के बारे में है, that might be helpful. बट सारे चीज़ इलेक्ट्रॉनिक्स हैं, so if you don't get enough copy, it's fine. Thank you.
Thank you, sir. Next, we open the floor for feedback from our participants. We would love to hear your thoughts and experiences from this program. Please share your views. How did you feel about the program?
So good afternoon, everyone. I'm Simran Maratha, research scholar in the Department of Environmental Science, School of Earth Sciences, Central University of Rajasthan. So we have come to the end of this 5-day learning program, and first of all, I would like to thank the organizers and facilitators for putting together this 5-day networking program on renewable carbons and fuels from organic waste. So from our expert speakers and their engaging lectures, we have learned to manage the waste and to trace the carbons, to store them and to utilize them. So some of us who are already working, we got insights over fundings and the research protocols that where can we learn more. And to the new upcoming environmentalists, they got insights and upcoming opportunities that from where they can start their own journey. So I would like to thank all the participants also who have patiently listened to this, and thank you to the organizers, Dr. Bhagwan sir, Garima ma'am, and all the faculties for giving us the opportunity to learn and to grow together. Thank you everyone.
So it's good afternoon, all of you. First of all, before any feedback now, let me thank you all the coordinators, the school, university management, then the success behind the students, actually students who work to have a success on it. Thank you very much for providing such a good platform to learn this type of programs or complete this type of programs. Coming to the feedbacks, already we submitted it, but let me begin with the aim of this program GIAN course, that is networking. Professor Sandeep Kumar said on the first day itself. So that we have achieved, I think, to almost, and further we can go to RDTOP. And I'll take some quotes from Dr. Devesh Sharma, the Dean of the school. He said about this 5 days program, but this is not enough. We have to carry forward from here onwards. So if we are going to apply the text or technology what we have learned here, then that is actually the success. Then I'll go to Professor Rajesh Kumar. He said about the bag full outcomes of this program. Yeah, definitely, Professor. I have 4 to 5 bags takeaways from this event. So I'm going to carry forward these programs, and definitely, yes, we'll grow together by this type of programs. Thank you very much.
Thank you, sir, for your feedback. We would love to hear from other university students, participants as well. From our department, from our university. Yeah.
Hello everyone, my name is Naveen Yadav. I am from PhD scholar from University of Delhi. So first of all, I would like to thank the coordinators for organizing such a insightful event. So we have a lot of learnings, lot of information from here. So thank you everyone for being.
Thank you. The floor is also open for the faculty members to share their views. How did they feel about the program? Their takeaways?
Okay. First of all, thank you very much for sorry, my voice is today giving us a very nice opportunity to be part of this international program. So since last 2 days, like 5 days, I've been with Sandeep sir, and this is like my first experience regarding the foreign faculty from Indian origin. So in Pune, I've been received many faculties from the abroad of Indian origin, and I have seen their attitude towards Indian. Like I never seen such attitude like shown by the Professor Sandeep sir. He was down to that, and literally he's inclusive. He's the best example of inclusiveness. So he was like basically always saying that I would like to interact with students, I would like to bring them to higher level at international level. And I think we should have such kind of the foreign faculties, and in order to develop the education system of India, because we are lacking in many part of the education. And I hope in near future also we are going to have help from the Professor Sandeep sir. Thank you very much.
Thank you, sir, for your feedback. Yes, sir. Yes, sir, please.
हमने लोगों की बातों को सुनने के बाद जो महसूस किया है, अब उसके बाद के अपने उद्गार बताना चाहता हूँ। जैसा कि प्रोफेसर संदीप भाई ने कहा कि उनको दो चीज़ें अच्छी लगी। एक तो पधारो हमारे देश, क्या बात है, बहुत अच्छा लगा सुनकर के सर। अब हम भी राजस्थानी हो गए हैं, इस भाव को हम बेहतर समझ सकते हैं। दूसरी बात थी कि हम लोगों का जो कोऑर्डिनेशन था, ये भी उनको बहुत अच्छा लगा, और उनको भी एहसास नहीं हुआ कि 5 दिन कैसे गुजर गया। तो आपके एहसास के लिए मैं बताना चाहता हूं कि ये 5 दिन गुजर गया है और आज हम बिछड़ने की स्थिति में हैं। पर मैंने सुना है किसी शायर से, वो कहते हैं विरह तो मिलन का मार्ग प्रशस्त करता है। तो इट्स एन गोइंग टू बी अनदर अपॉर्चुनिटी टू मीट अगेन, सो इट्स नॉट दैट वी आर सेपरेटिंग विथ ईच अदर। और तीसरी बात जो भाई साहब ने कहा, नाम मुझे ध्यान नहीं आपका, जो अपने बैग्स के बारे में मेरे रिमार्क्स को लिया, बहुत धन्यवाद, बहुत विजिलेंट हैं आप, पहले तारीफ करना चाहता हूं। और आपने कहा कि 4 या 5 बैग लेकर के जा रहा हूं, नॉलेज, फुल ऑफ नॉलेज। तो मुझे लग रहा है कि इसी तरीके से डिस्ट्रीब्यूशन हुआ था, हर दिन एक नॉलेज बैग दिया गया है। संदीप भाई, थैंक यू सो वेरी मच। एवरीबडी हैज टेकन 1 बैग फॉर 1 डे, सो बिगर प्रोग्राम विल गिव बिगर बैग्स ऑफ द नॉलेज, but still there are courier mechanism, and that is through the online courier mechanism. The knowledge can be shared still if you have the willingness, and I hope संदीप भाई ने पहले ही कहा है कि मैं आपका वहाँ पे स्पोक्समैन होऊंगा, तो इसका मतलब है हमें निराश नहीं करेंगे। जिस किसी की भी जरूरत हो कुछ और बैग मंगवाने हो नॉलेज के और किसी चीज के नहीं, तो यू कैन राइट अ मेल टू हिम, यू विल फाइंड द बैग्स रीचिंग टू योर होम in your mailbox. Thank you so very much everyone. Enjoy this.
Thank you, sir. Following that, we now proceed with certificate distribution. I request all dignitaries to please come forward. Yes. Mr. Ayan from Central University of Rajasthan, please come forward. Yes. Please come forward as I call out your name. Miss Banashri Soren. Mr. Basant Bijarnia. He's not there, okay. Dr. Vibhuti Bhushan Sahu from VIT Tamil Nadu. Ms. Bonu Shelja. Ms. Charulata Sivodia. Ms. Chavi Saini. Dr. Dharmendra Kumar from VIT Tamil Nadu. Dr. Smita, Central University of Haryana. Dr. Pankaj Kumar from RSPCB, Jaipur, Rajasthan. Dr. Vineet Kumar, Central University of Rajasthan. Mr. Hemant Kumar Virat. Mr. Himanshu Somawat. Mrs. Jagriti Dadwal. Ms. Jyoti from Central University of Haryana. Ms. Jyoti from Central University of Haryana. Ikra Chaudhary. Ms. Jyoti Bijarnia. Ms. Ikra Chaudhary. Ms. Kirti Lakwal. Mr. Kuldeep Chaudhary. Mr. Lalit Kishore Bagra, University of Rajasthan. Ms. Mahima Yadav. Mr. Muhammad Midlaj. Ms. Muskan Chaudhary. Mr. Yaveen Yadav. Mr. Naveen Yadav, University of Delhi. Ms. Nazia. Mr. Umair Bhatt. Umar Ahad Bhatt. Mr. Om Prakash Chaudhary. Mr. Pradeep Yadav. Mr. Piyush Gujar. Ms. Preksha Palsania. Ms. Renu Meena. Ms. Ruchika Agrawal. Mr. Sanjay Anand. Mr. Saurabh Chaudhary. Mr. Saurabh Shekhar. Ms. Shalini Satya. Mr. Shubham Kumar. Mr. Shubham Parsoya. Ms. Simran Maratha. Ms. Swati Verma. Mr. Tarun Kumar Saini. Mr. Ujjwal Parikh. Ms. Vartika Tripathi, Ms. Yashika Chaudhary,
Ms. Jagriti Verma from Central University of Rajasthan. Ms. Nidhi Singh from Central University of Rajasthan.
Thank you everyone, thank you dignitaries. To formally conclude the valedictory program, I now request course coordinator Dr. D. Bhagwan to deliver the vote of thanks.
So good afternoon everyone. I will not take much time because we are hungry. So just I will finish as soon as possible. So respected dignitaries, our esteemed guest and distinguished speaker of this GIAN program, Professor Sandeep Kumar sir and Devesh Sharma sir, Dean School of Earth Sciences, Professor Rajesh Kumar sir, Director IQAC and Professor of EVS, and Professor Lakshmikant Sharma sir, Head of the Department, faculty members of the school, participants and my dear students. So as we came to the end of this wonderful GIAN program, it's my honor to deliver the vote of thanks on behalf of organizing team. So first of all, we would like to thank Professor Honorable Vice Chancellor Professor Anand Balarao sir for giving his motivation and his strong leadership, constant support to make this event possible by providing all the infrastructure facilities and necessary approvals. And a very special thanks to Professor Sandeep Kumar sir and for his valuable international insights and his constant support. So from morning 9:30 to, if I ask for sir, you have to complete up to 5:30, 4:30, he will extend as per the requirement. Like without any hesitation, he has taken all the lectures which we have planned, and upon request, sir has also interacted with all the members, those who are interested to, or those who have like any suggestions, guidance, career guidance. So all the things has been taken place during the course simultaneously, and some of the discussions has also been carried from the university administration, where we are planning to, some discussions were also initiated to have some joint programs between ODU and CURAS. So it is the initial stage where we are building network. So it may carry forward and maybe future students may get benefited. So that is also one of the insightful we have benefited along with lectures. And we also very thankful to the local coordinator GIAN, Professor Sanjeev Kumar Panda sir, for his helpful guidance as well as timely support for organizing this course. And our heartfelt thanks to Dr. Devesh Sharma sir, Dean School of Earth Sciences, and Professor Lakshmikant Sharma sir for their continuous support whenever I request them for any matters related to GIAN program. Always they give guidance as well as suggestions and pathway. They show you, if you go through this way, then your program is going to be smooth. So likewise they have been given guidance as well as for even their presence during the program. So thank you, sir. And once again, I would like to thank Professor Lakshmikant Sharma sir for contributing his insightful lecture delivered today. And we also thank Professor Pramod Kamble sir and Professor Abhishek sir for delivering valuable lectures. And special thanks to Abhishek sir, because Abhishek sir and his team, Manipal University, because they have provided us their lab facilities for demonstrating, because here we had 4 days of lectures, and once we visited the lab facilities, so we can have a correlation between theoretical as well as practical aspects. So that was like benefited a lot us. So thank you for Manipal University administration, and special thanks to Professor Rajesh Kumar sir and Dr. Garima Kaushik madam, co-coordinator of the this GIAN program. So they always create confidence inside me. Sometimes I will become like nervous, I will feel nervous. So always they gave prompt response and positive signs to like you are able to carry this work, and if you need any help from our side, from administration side, so Professor Rajesh Kumar sir, he has given, even sometimes I am unable to deal with administration, so he has coordinated, so thank you sir. And a big thanks to all the faculty colleagues, Dr. Ritu madam, Shailesh Patidar sir, Nivedita madam, Subrat sir, Chinmay sir, Jayanti madam and Jayaprakash sir for always like being a strong support for organizing this networking conference, networking course. So we are grateful to even IIT Hyderabad, Professor Anil Agarwal, National Coordinator and his team members, Balachandran and Anjana for their esteemed coordination as well as cooperation. And Ministry of Education for initiating such a networking program where we are going to build international network, and which will be having like sharing of academic networking and R&D networking. So I also would like to thank my mentor, Professor Himabindu, because like at this GIAN knowledge I have gained from my mentor. So I always thank her. So special thanks to Vice Chancellor Office and Registrar Office, Finance Office and University Administration, ICT Cell, especially Vivek ji, and guest house staff, all supporting staff of school for helping and planning and smooth execution of this course. And we also strongly appreciate the hard work of volunteers. Just I am here standing because of the volunteers, those who are working for like even sometimes I message them at night 10 o'clock, 12 o'clock. Today, unfortunately, I used to call them at 4:30, 5 o'clock. So that, but still they're responding to my call. So I can't, like, without them, I am not going to organize this. So special thanks to Jagriti, Ikra, Jyoti, Basant, Saurabh Shekhar, Shalini, Preksha, Swati, Jagriti Verma, Omar, Kuldeep, Kirti, Nidhi Singh and Mahima. So they constantly supported. So because of that, we are reached to the valedictory session. Last but not least, all the participants, and especially the other institute participants, those who came here and they spent for 5 days. So for them, thank you for their active participation as well as interaction. So this interaction has to be continued for the longer time period for the future, and you need to have networking, and hope you may have next GIAN program along with Professor Sandeep Kumar sir. This is one of the, like if it happens, then that will be the one of the good outcome from this. So thank you all, and thanks once again. Thank you all, and thank myself as well, because I am also human being. Thank you.
Thank you, sir. And thank you everyone for being a part of this wonderful GIAN program. Wishing you all continued success and many and meaningful journeys ahead. Have a great day. And I request everyone to proceed downstairs for lunch. Thank you.